Yes. Okay, let's start. Okay, so it's the very first time I teach this course. Okay. So we'll see how it goes. And don't hesitate to ask questions if something is not clear or you need more explanation or something. We have time. I think we have time. I try to time it a bit. And we have time for questions and so on, no problem. So don't hesitate to ask any questions. Okay, does everyone has the data we'll use for the tutorials? Okay, very good. Okay, I will start with some introduction and a bit about the format used in the package. And then we'll talk about the real analysis. So processing a population structure today. I think we'll have time. And tomorrow, GWAS and pushing scores and so on. Okay, so the main motivation for developing the two packages. So yeah, I really wanted to do all my analysis in R. And I was a bit frustrated by using all the different software because like when you use command line software, like Pling, for example, but many others, usually they have some different input formats. So you have to convert when you go from one to the other. And also something I find a bit annoying is you need text files to pass the parameters sometimes. Yeah, which I don't really like. This made it hard for me to do a chain of analysis, perform some exploratory analysis, even use. So I know a lot of R code and R packages I'm familiar with. So I just would like to use them when I can. So it's easier for me if everything is in R. And also because I'm working in like, I want to develop new methods. It feels a bit hard to work on you know, binary files like the bedbeam files, the Pling files, if you know that. It seems a bit hard to develop some new method on this. So I developed this simple matrix-like format I will explain in a bit, which made it much easier for me to code and access the data. Yeah, so I just developed this package like more than 6 years ago now. I started. And at some point, I realized that many functions in there, like for example, when you do a GWAS, you take every variant, every column of your data one by one and do some association tests with some phenotype. But you could want to do that with other types of data, like other omics data, for example. So it's not really specific when you do these multiple tests. Taking one column by one column is not really specific to genetic data. You can do a TWAS, for example, a EWAS, transcriptomic expression. And for example, PCA is the same. So in genetics, we use PCA to get population structure. We'll see this in this chapter 5. But actually, people run this PCA on methylation data also, and other types of data. So I just realized that all these functions are not really specific to genetic data. So I put everything in another package, which is called bigsnpr. And basically, all the functions that are not really specific to genetic data are in this package. And then the functions that are really specific to genetic data are in bigsnpr. Okay. So if you have large matrices, even if it's not genetic data, you can still use this package. Yes. First on this. And to know from which package the function are, it's supposed to be easy. So the one starting with b underscore are from bigsnpr. The one starting with snip underscore are from bigsnpr. And the bed underscore also from bigsnpr, and it's to be used directly on bed files. We'll see in the population structure part. Yeah. Any questions for now? So there are actually many features now because I said I'm developing this package. I've been developing this package for like 6 years now. So it's Many things are in there. So there are package websites for the two packages where you can see. So this is the package website for bigsnpr, for example. You have here a list of all the functions that are available. And so, for example, if we go quickly, you have these two functions, univariate linear regression and univariate logistic regression for the GWAS, we'll see. You have sparse linear regression, it's to make a penalized regression from your data. You have some function for computing SVD or PCA, which is the same. Some matrix operation like some correlation, some matrix products, and so on. A bit of plotting and predicts for the prediction methods. And then some utilities where you want to compute some statistic, for example, the standard deviation of all the columns or things like that. To read from a text file, to write to a text file, and so on. We'll see some of them in the course. Okay. And then you have some vignettes, so some small tutorials. We'll also mention some of them during the course. Okay, so this is just bigsnpr. You have bigsnpr. The same, so you have some function for reading. We'll see again from bed file, bgens files. A bit to do some QC rate-net imputation. We'll see also this in chapter 4. To handle LD, so correlation between the variants, do some SVD or PCA, compute some LD score regression, and then a few methods for computing polygenic scores, so genetic predictors. Some methods for multiple testings, and again, some other utilities. So there are many things. And also you have some functions specific to bed files. So to be able to directly run this function on the bed file, the plink files. Okay, we'll see that. And again, you have some tutorials, the vignettes here. Okay, and another way to present the different features that you have. So you can perform some polygenic risk score, so polygenic score, risk score when you talk about risk of disease. So what is available? So you have penalized regression, so to directly train some model on the genetic data. So if you have the genetic matrix and a phenotype, you can directly build a predictor using the individual level data. Okay. But most of the polygenic score are based on GWAS summary statistic. So instead of having the individual level data, you just have the summary statistic, so the effect size from the GWAS, for example. And to do that, you can do C++, clumping, and thresholding. I will explain later. DPRED2 and LASSOSUM2, which are two methods that work very well for that. What is missing for now, that will work later, one is the multi-ancestry training. So you can't really do that yet. For population structure, you can do the PCA. You can also, we'll see, infer the ancestry of individuals. So for the GWAS, we can do linear logistic regression. There is no mixed model yet. You can't really do any rare variant association when you gather many snippets. You can compute some correlation matrix in sparse formats. You can split this in LD blocks that are independent. To estimate stimulability, you can run LD score regression. I just have a reimplementation of LD score regression in the package. Now you can also use LD auto for that. The same for estimation of geneticity. If you want to estimate genetic correlation, I don't have anything yet, so you should use something else for now. For fine mapping, so LDPRED2 gives you the probability of being causal per variant, which is what you need for fine mapping. So it can be used for that. And for now, what is missing, the GWAS summary imputation. Mendelian randomization, I think will never work on this because it's completely different from what I do. So if you want to know about Mendelian randomization, there is Xiong that works on this. So you could ask Xiong to help you with that. And some other things like integration with ink, format conversion, and so on. Okay, so we'll try to see most of this. So to get some code example, you can find many. So the first thing that you should do when you want to try a function is to look at the documentation, especially at the section of example at the bottom. You know, when you do of the documentation, the parameters that you can use, and then at the bottom you have some examples that you can try to give you an idea how to run the function and what you get from it. As I explained before, there are some tutorials which are here in the vignettes. Usually there is one for each paper, so each method, and there is one tutorial available. So, and I provide some link from this tutorial here. So there are some other examples I will see here, for example, here and here. Again, some other tutorials. Basically, you have two tutorials on the same thing each time. And also, if you look at one of the papers I mentioned, the code for my papers are available on GitHub, so you could you can reproduce or get inspired by the code there if you need. Okay. Any question? So we install the package. It should be easy. So they are both available on Cran, so you could just use install.packages. So it should be very easy. If you need the latest version, you can install from GitHub using remote install GitHub. Okay, it should be fairly easy to install the packages. It should work very well. So no one had any issue, right? Installing the package. Okay, that's fine. Yeah, just try to write the name of the methods properly. So big stats with no uppercase or whatever. LD price is just LD uppercase. Okay. A quick introduction. Now I will just introduce a bit the inputs and formats. So the format used in bigsnpr is called a fallback big matrix. So it's called a FBM. So basically it's an on-disk matrix format. So the problem of working with R matrices is that they get very large very quickly, and then you don't have enough memory to really store them, the random access memory, right? But instead, if you store this on disk as a binary file, then you have basically unlimited space, or almost. Then you can access the binary file on disk using memory mapping. So this is what I implemented. And what is memory mapping, to give you some intuition? So you have your matrix, which is basically stored as a file on the binary file on disk. So when you access the first element, which is the first row, first column of your matrix, basically when you access some data from a disk, for example, even from memory, you access a block. So let's say we access the first column, which is the first block of the data. So when you access the second element, which is the second row of the first column, it's already accessed in memory because you access the first block, you access the first column entirely when you access the first. Okay, so it's already in memory. It has been read from disk to memory, and it's kept in memory. So you can access the second column like this. The second time you access the second column, it's already in memory, so it's very fast. Okay. You can access many columns until you don't have enough memory to keep all these columns stored in your memory. Okay, and then some space is freed automatically so that new columns can enter the memory. Okay, but you don't have to think about it because it's seamlessly managed by the OS, so you don't really have to think about it. It just works. And this memory mapping from disk is very convenient also for parallelism because the data is shared between processes, so that when you have some code that runs in parallel, the data is not copied to each process. It's just accessed from some shared memory. So you don't have to copy the data, which makes the parallelism more efficient. Okay. So you can actually store many types in your matrix. So we'll see. We're mostly interested in the last one, but you can just store some doubles, which are the standard, floating point numbers. You can use the single precision if you want. You can store some integers and some smaller integer. For example, you can use this format. So you won't really see it, but it's the format that is used in bigsnpr, where you can store basically from 0 to 255. Then we'll see how I use that to store dosage data, but requiring only 1 byte per element, which make it smaller than the standard matrices, for example, that use 8 bytes per element, which is 8 times more, right? So it's just in big data. So you can have any matrix in this FBM format and can use all the bigstats function on it. It has nothing to do really with genetics. You can use it for anything. So now specific to genetics bigsnpr. So I have this object called bigsnp, which is just a list with 3 elements. You have the genotypes, which is basically the matrix of genotypes. It's this FBM with 256 values. Also, you have a FAM component, which is just a data frame storing the information on the samples, the individuals. And then a map data frame storing the information on the genetic variants. Okay. And then to store the genetic data, as I said, I can store 256 values. And I use this code to store any value I want. So I store these values here. So the first 4 is to store some genetic code are equals 0, 1, 2 RNA. It's what you get from Plink, for example, the 3 values that you can get. The next 3 is to store some imputed data. So to distinguish between having the calls here or having it imputed here, it just makes it convenient sometimes. And then you can store values from 0 to 2 every 0, 0, 1. So it's a way to store dosage data from that to decimal places. So you can store with this format, you can have dosage data, but it will be rounded to decimal places. Okay. So from 0 to 2. And then because there are only 256 values, as I said, we need only 1 byte per element, which makes it 8 times less than the standard, floating point numbers. But it's still 4 times more than the bed format, because in the bed format you store with 2 bits, so you can store 4 values per byte. So it's if you use bed files, it's like 4 times. The size is 4 times less. It's more compact in some sense. but in the format you can store only these 4 values. You can't store the dosage data. Yeah. Any question? And as I said before, you can now there are also functions to work directly on bed files, so you don't have to go through these formats for some of the function. You can directly apply them on bed files directly, and we'll see in the PCA chapter we will use them. So the question next is how to get this format. So either the FBM if you work only with Bigstata, or the full BigSnip object with the FBM, the genotypes here, and the FAM and map. So if you just work with matrices, you can just convert a normal R matrix with SBM. You can read from large text files with this function. If you have a CSV or TSV file that is very large, you should be able to read it as a FBM using this function. But remember that in a matrix, you can store only numeric data. You can't store, strings or whatever. It should be all numeric, right? All numeric values. And then there are functions. So in bigsnpr to read from the ping files, so the ping files. So you have snip read bed and snip read bed 2. So the second one just allows you to read a subset of individual and variants if you need. And also use parallelism. So basically, use the second one. And what you get then is this. So this is basically corresponding to the bed file. This is corresponding to the FAM file. And this is corresponding to the BIM file, right? So you basically get the same thing, but in as a data frame here and FBM here. You can also read from bgen files. So for example, the bgen files, it's the format used for UK Biobank to store the imputed data. And so I've made this function to read from the bgen files. So to read, you read the dosage, it's in imputed data, so you can read the dosage, so a value between 0 and 2. And it should be fast enough. So it takes about 40 minutes to read 1 million variants using 15 cars. Okay, so for example, to read the UK Biobank files, imputed data, you can just use this function.
So that because it makes a copy elsewhere.
It's to convert into the bigsnp format into this FBM plus map file.
That puts it another way.
It just converted to the format that are used by the package, because otherwise it's a bit complicated to work with. It's a compressed format which is a bit hard to read. Yeah, so it just converts to the format I'm using in bigsnp. Then if you need to read more formats that are used in genetics, for example, I had to do this for the ISAC data. So the ISAC data has been imputed. We'll talk about it quickly in the end, because I think many people work with ISAC here. That has been imputed with the recopy pipeline, so you get it in Oxford format, I think. So one way to, it's a bit more complicated, but one way to read any genetic format is just to use Plink. So in Plink, you have this recode function or option that you can use to write some any format into a text file. So into dosage, it will start like dosage, but in a txt file, basically. Then you can read this txt file from using this function, for example, in R. Then you can use the dosage that you just read to fill some part of the FBM. So it's a bit more complicated, but you can see an example here of the code I used to convert the ISAC data into my format, which is now available on GenomeDK and Statistic Denmark. Okay, so basically you should be able to read from any format into the format I'm using in the package. So what are the formats that you use usually? Are you using Plink or? So the main problem with Plink, the bed format, the first one, now they have the pigeon format. But the bed format, the main issue is that you can only store 0, 1, and 2s. So if you use imputed data, you will lose some information in some sense because you have to round. So yeah, but I don't know if you lose a lot of, power, for example, in GWAS by you losing the information by rounding the genetic data. I think it would be something that we could try. Are you doing that, Oli? To test the GWAS power, where you use different methods or?
Sure.
Yeah, if you compare, like, for example, using dosage data versus using the just 0, 1, and 2. Yeah, I think we talked about this with Bjorn at some time. Yes. Okay. Now I will explain a bit how to work with the M, which is this matrix format on this that I'm using in the package. So for now, it's just using this so you can make a FBM like this, for example, with 2 rows and 5 columns. Just something very quick. You need to specify a backing file because, as I said, it's a binary file on disk. So it will actually store this in this .bk file. So you provide the prefix, and then you will make the .bk. Okay, so the bk file will be the binary file storing the data that is in the matrix file. Okay, so we can maybe try this code. Yeah, and here in the end I use this save method, and what it does, it makes this RDS file. So you have 2 files. You have this bk file, the RDS file. Maybe I can make it larger. Okay, you have these 2 files now, bk and RDS. So the bk file is storing the data, the matrix. The RDS file is storing all the other informations, like the number of rows, number of columns. Basically, is basically storing this object X, so that you can, in another session, you can read it again. So, for example, if I am restarting the session, okay, I don't have X anymore. But what I can do is using this big attach function to just read the RDS file and reconstruct the FBM. Okay, so I need to load that. Oh, yes. Yeah, and now it's there again. So basically, you have to make the FBM only once. So for example, when you read from snip read bed, it will make these two files, bk and rds, and then you need to do that only once. You need to read convert from the format only once. And then you use either big attach if you only store a SBM, or snip underscore attach if you use a big snip, which what you will get in a what you would get in a use read bed or read bgen. Okay, let's make I'm just removing these files. Yeah, I can do that in Windows. Okay, let's make it a bit larger. Okay, so you can see that the BK file now is much larger because we have more elements in the matrix. But then the RDS file is still very small. Okay? The RDS file is just storing some information about the data. It's not storing the actual data. So this object here in memory, it's very, very small. Okay. So the data is not in memory, it's just on disk for now. And if we want to access it in memory, so let's we can actually access the full data. So you should basically never do that, but let's do this. We can access the full data using this square bracket. And you can see now it's just some standard R matrix with 10 million elements. And if you look at the object size of this matter, so just to make you realize that the SVM object is very, very small. It doesn't take any space in memory. The actual data is stored in the big file. And then you can access the data via memory mapping, but you don't really have to think about it. You can just use accessors that are similar to the accessors from the standard R matrices. So for example, I can say, oh, I want the first two columns, and then you access this as a R matrix, but only with the two columns, the first two columns. I can do the same with the first two rows if I want. Okay. So let's do it like this. So I can access the first two rows, first 10 columns if I want. So it will access from the disk file to just a standard R matrix. Okay. A subset of the data as a standard R matrix. Yeah, so it's fine to access columns because columns are stored contiguously. So you have a matrix, you have two dimension, but you have a binary file on disk, which is just a long vector in some sense. And the data is stored. So you store the first column and then the second column, third column, and so on. So each column are stored contiguously. But if you access, for example, the first row, as I said, when you access the first row of the first column, you access the whole column. When you access the first row of the second column, you access the second column entirely, and so on. So basically, accessing the first row is basically accessing the full matrix from disk. Yes, so you just read from this the full data, which can be very bad. So try to always prioritize accessing columns, a subset of columns instead of a subset of rows, if you can.
But then
No, you have to. Usually, you work with columns for example, if you want to, usually you work with columns, so it's not a problem. But I will try to explain a bit in some other examples. Yeah, but try to work with columns as much as you can. And you can access the full, if you really need, you can access the full data as a standard R matrix just by using the two square brackets without anything inside. Okay. You should always access a subset of columns if you can, because the data is stored column-wise. Yeah. And if you access a subset of rows, it will read non-contiguous elements from the whole matrix. Okay, so what if you want to apply some standard R function to this data? For example, if you want to get the call sums, the sum of each column of your data, so you could do it like this: access the full data as R matrix, and then just use the this R call sums function to get the call sums. Okay, but it's not good. So an easy way to do that is to do that efficiently is to use this split apply command strategy. So you split, for example, with 1,000 columns max per block. Okay. You apply to the first block the function you want. So here the call sums, and then you combine the results. So here you get a vector of 1,000 values, and then you want to combine all this result from each block by just concatenating to get the full vector corresponding to all the columns. Okay, so it's very standard to work on very large data, this split apply combine strategy. And actually, so I made a function called big apply to make it easy for you to do that. So you don't have to split yourself, get the indices corresponding to each block, then apply the function and then combine the results. If we look quickly at the documentation, so you have the first parameter is just the FBM. Then you have the function to apply that you need to apply to each block. You have the parameter for which function you want to use to combine the results. And then you can also you have also the block size, which is the maximum size of the blocks that you want to access. It should be automatic. That should be a default value for that. It should be good, so you don't really have to think about it. And then also you can do that in parallel, because you can just you can have one process that works on this block and then another one in the meantime working on this block. So it can also be done in parallel. You just have to specify this endcores. Okay, let's there's a tutorial that you can find in bigsnpr on working with a big apply. If you need more examples on how to use it, tutorial here. Okay, let's try to take this data. So we can restart if we want. When I restart, I just clean the session, because it's something that should always do in R. When you go in RStudio, you go to the global options. You should always, it's a good practice to install your workspace, the data in your environment, right? The data you work with. You should never store them when you close RStudio. It's a good practice to always start with a clean session for reproducibility and so on. Yeah, so you can say never here and don't restore our data. So when I restart the session, I just clean the session. I don't have anything anymore. So for example, X is not there anymore. So just take this data. So it's just a smallish data with like 500 rows and 4,000 columns. And I want you to try using big apply, compute the sum of each column. Okay, so you can look, we can take maybe 15 minutes, and you can look at the documentation of this function to understand what you need to provide. And you can look also at the examples at the bottom of the documentation. Okay. So if we look at the documentation, the example, the first one is just getting the mean of each column. So for that, you need to provide this function where you have x in this int parameter, which access the columns corresponding to these indices. So you just access a block of columns, and then apply the function to it. So for example, if I run this, I don't know, like one, and okay, just give me the mean of each column. So you provide this type of function to this parameter. And you need to provide how you want to combine the results. So here we just want to concatenate the results. So we can just use this function C, which is just the C concatenation from base R. Okay, so if we want to do it for the call sums, so here I just made this function before. So actually, you don't need really to do that. You can directly make the function like this. You can create an unnamed function in R, right? You can just use it like this. So here we want the call sums. We want to combine. So if we don't combine, what happens? So if we don't combine, we get a list of 1. So what is this list of 1? Why 1? It's basically the number of blocks that were used. Because the data is not very large, it didn't really have to split to access the data into like smaller blocks because the data is quite small anyway. So if I specify the block size by something different than the default, for example, let's say 500, you can see now that I have a list of 10, where each time I have less than 454 values, so less than 500. So this is the max size of each block. And because the data has like that many columns, it just makes 10 blocks about 454. Okay, so if I don't provide this the combine, I just get a list with the result of each block. But then if I use combine called C, then I just get one big vector with all the results concatenated. Okay, so it's just a way to easily apply some standard R function, some blocks the splitting, apply the functions, and then combine all the results for you. Okay, I will quickly talk about RCPP. I do realize that many of you don't really use RCPP. So RCPP is just a way to write some C++ code that will be available as a R function. It's just a way to have some very efficient R function that are coded as C++ code. So you can also access this data in RCPP. I will just quickly explain if you need to do that at some point. So you just need these first 3 lines to access this accessor that I will use here. And then you make a function called here bcallSum that returns a numeric vector, just a vector of a floating point number. And the parameters of the function are this BM, which is just the FBM that will be passed to this. Then what you need to do is access the external pointer to the data, and then make the accessor from this pointer. So basically, you need these 2 lines, and then the 3 lines here. And then if you know a bit of RCPP, the code then is the same as if this would have been a normal RCPP numeric matrix. The RCPP numeric matrix is just the standard R matrix that are passed to C++. So once you've made this accessor to the matrix, the code here is exactly the same as normal RCPP code with the normal RCPP matrix. So you can get the number of rows, number of columns, and then loop over all the elements by just accessing the data with the parentheses. Now in C++, you use the parentheses here. So just the i's column and j's column. Okay, I won't, yeah. I'm not sure many of you use RCPP, but you know now that you can use RCPP and access it almost as if you had a normal numeric matrix. You can access the data from the FBM. Okay, and actually I use that a lot, make the functions in the package very efficient. I code a lot of the function in C++. So you use R function, but it's actually C++ that you use. And then many times we want to apply a function, but just on a subset of the data. So you could, copy the data to just use a subset, to just make a copy just with the subset of the data, but we don't really want to copy the data. So in all the functions that I have, usually there are 2 parameters that are called in row and in call usually. Sometimes for in row it's called in train when it's about training, so like some predictive model or something like that. You can use to use a subset of data without making a copy of the data. And to do that in C++, with the thing, you just pass the 2 vector of indices for the rows and columns. The only line of code that you need to change is instead of using this big matrix accessor, you use this sub big matrix accessor, and you just pass the indices you want to use. Okay, and then the code is exactly the same as before. It's just that when you will access these elements, it will access the elements corresponding to the subset of indices you provided. Okay, it's just if you need some RCPP at some point, just very quickly. So it's again to do the same thing, to get the callsum, right? And then what you could use also is some functions that are already implemented. So for example, I have this summary function called bigstat, which gives you a data frame with the sum and variance, so the sum of each column and the variance of each column. And then this big scale, so you have to use the parenthesis here. So this function will give you then the mean of each column and the standard deviation of each column. Okay, so if you need some summaries of each column, it's already implemented in these two. Yeah, it's because so big scale is a function with two parameters, center and scale equals true. And if you say scale equals false, for example, you would get a vector of 1 for the SD, for the scaling. If you use center equals false, you will get a vector of 0, because it's a function I use for applying some scaling inside some other functions. And sometimes I want to not scale, for example, the columns, or I just want to also not to center and scale anything. So I can just use false and false. And this big scale function is actually making another function, but that works differently based on these parameters. So when I say a big scale, what I get is the function, okay? That would work differently based on the center and scale. So for example, if I say, so here I get the mean and standard deviation, but then if here I say scale equals false, I actually get a vector of 1 here. And then, yeah, sometimes. Okay, any question on this part? So I just try to introduce a bit the format, LBM format that was used. Okay, let's talk about pre-processing. So I include like conversion, quality control, and imputation, basically. So we talked about some kind of conversion here when I talked how to get some bigsnp objects from bed files or bgens files, for example, or other formats. But so Plink, Plink is a very popular command line software, and it's very, very good for conversion and quality control. So at some point, I wonder, should I try to rewrite some of the Plink function in the package, or should I use directly Plink for these parts? And I choose to just use Plink because it's so good at it. So what I made a bit of some wrappers to Plink, so to be able to directly use Plink from R very easily. So I made a few, like for example, this snip Plink QC to perform some quality control. This King QC is for computing the relatedness based on this King robust chip estimator. Some IBD and so on. And to also make it easy to download Plink, I made some function to just download Plink from R. So you have both like Plink 1.9 and Plink 2.0, right? That are a bit different. Sometimes you have functions that are available here, but not here, and the opposite. Okay, so Plink QC to do some quality control, also to convert to BinFAM. So if you have something, other format that is like, I don't know, VCF, for example, or PED, you can convert this to BinFAM by using this. And at the same time, it will perform some quality control. So this King QC, there are two ways to use it. So when you use make bed equals false, it just gives you a data frame with all the pairs of individuals that are related to each other. And if you use makebed equals true, what you get is a new bedbeam file with where these people have been removed, the related people have been removed. So basically, in each pair, I think they take the second one and just remove these people, so that you don't have any related pairs of individuals anymore. Okay, so makebed equals true is just making a new bed file without any related people anymore. And with makebed equals false, it's just to put a data frame with all the related pairs. It's, for example, what I use to compute the relatedness that is available on GenomeDK and in statistical Denmark. And with kin coefficients, so actually 0.5, when you get a kinship of 0.5, it actually means that it's the same individuals. So either duplicates or monozygotic twins. Then if you have 0.25, it's like siblings and parents. Okay, so a child and a father or something like that, or two siblings. Then you have like second degree relatives, for example, grandparents and uncles, aunts and so on. And then third degree relative, which would be the first cousins. Okay, and usually the threshold that is used with king, it's either 2 to the power minus 4.5 to get rid of all these related individuals, or 2 to the power minus 3.5 if you want to keep the cousins. Okay.
So I have a question. For this QC, does it use the default parameters that the thing actually uses, or do you define the parameters?
Which parameters?
The pink QC, the first one.
But which ping parameters are you talking about?
It could be anything.
You mean to do some quality control?
Yes.
Okay, so to do some quality control on the, I will show later, but the quality control on the minor effects and so on, it's this function. And this one is to do the relatedness threshold, right? So basically the only parameter you have is the threshold that you use, which is just a parameter of the function. Yeah.
But for the QC, so the one above that.
Yeah.
You get to define parameters.
Yes, I can show you. Just load this pink QC. And so for that, you need the pink file, right? The executable, and the prefix, the bed file that you, or the BCF or whatever. The file type, which is a B file, so the bed file, or it can be VCF, it can be a file for pet files. And then you have the manual frequency, which is I think it should be the same default as Plink. The default that I used should be the same as what they use in Plink. So some filtering of missing values for the variants, missing values for the individuals. You have the Hardy-Weinberg equilibrium. So this is not the same default. I don't remember the default for Hardy-Weinberg, but in the end, you can choose to keep autosomes only or not. And then you can provide any, if you need more parameters in your command line, you can just provide them as an extra string if you need more. Yeah. And for the snip Plink QC, so you have the path to the Plink 2. So you need Plink 2 for that. The path to the first file. And then the threshold you use for the kin coefficient, whether you want to make a new bed or just report the data frame, you can do it in parallel when you run Plink. And again, extra option if you need more options.
When you look at the label,
I think it's for each pair you remove the second one. Yeah. I'm not sure if Plink does that. I think people have tried to design such algorithm that you keep the maximum number of people. But I think you should use something different, right?
I always do. There's, as Lauren said, if somebody is older, I never use the algorithm. And then maybe favorite.
Yeah, honestly, I just removed the second one in each pair and don't really think about it. I'm not sure you can keep a lot more by having an algorithm that just picks the maximum amount of people. Maybe you would get, I don't know, 1% more. I don't know. I'm not sure it will make a huge difference. Just to explain to everyone, for example, if you have some curve like 3 related to 1 and then 3 related to 2, if you remove the second in each pair, you would remove 1 and 2, right? But you could, in theory, remove 3 and then keep 1 and 2, right? It would be the same. And I think there are some algorithms to try to pick as many people as possible while getting no related pairs anymore. But yeah. Then if you need to use other Plink functions, what I do again, I do it from R directly. So I use system calls and package glue. So system calls is just to call some command line code directly from R. And then glue is just a function from this package glue to make it easier to write some command line. Then you can specify between the curly brackets. It will basically take this Plink and look for the variable called Plink here and replace this with the content of the variable. So it makes it easy then to write just a big string where you can have variables that you put within this curly braces, and it will just replace them. So it makes it easy. Otherwise, you have to, you could write this. I can show you this. You could write, paste Plink. Then it starts to be complicated when you have many things where you have sometimes variables, sometimes strings. When you do it like this, you just have one big string, and it's everything is written as one big string, but then the variables are replaced by their values inside. Okay. So if you want to use Plink or any other, I do that also with when I need to call some Python code. I just call Python here and all the parameters and so on, directly from R, so that I can just have a script with all my code. I don't have to have another script for Python or script for some command line or whatever, some bash script or whatever. It's much easier to code everything in R. Okay. So now that you've converted and do a bit of quality control, you might need to do some imputation. So most of the function in the package don't really handle missing values. A few of them do, but most of them don't. So you need to either impute. For example, in bigsnpr, if you use the format that bigsnpr uses, you can impute very easily, simply with this function. You can impute by the mean, by the mode, by the median. You can choose whatever you prefer. There is also a fancier function that use XGBoost, so it's a machine learning model to impute from the, so where you take a genetic variant, you look at the ones around that are supposed to be correlated, and you learn from the others to impute the one you're interested in. So it's a bit slower, but it should give you better imputation if you need a better imputation. And when I talk about imputation here, I'm talking about if you have a few missing values, you want to fill the missing values, right? I'm not talking about imputing completely new variants, right? It's a different problem. And to impute from an external reference panel, if you need to impute many genetic variants that you don't have in your data, you should use the standard tools for that. I think now they have servers to do that, where you just send the data and they do it for you, if you can send the data. Otherwise, I think for ISAC, they did it locally in GenomeDK. So of course, if you have this kind of imputed data that has been imputed from some external reference panel, it's even better. Okay, so for example, if you use the UK Biobank, just use the BGen format, the imputed data directly, instead of using the bed file from the genotype in chip. Just use the imputed data, right? Just use the BGen, because then you don't have any missing data anymore, and it's just dosage that you. Okay, let's write a bit of code. So let's first download some data. So normally everyone has the data. If you are depending on when you are, make sure it's in the folder called TMP data. So that when I do this, so here I'm here. So you have this folder called TMP data. And I already have this zip, GWAS data zip here. So when I run this run once download file, it will check that the data is already there. And if it's already there, it doesn't download it because it's already there. When I run this, I don't download anything, right? It's just realizing that the data is already there. And then in the zip, I have just the path to the data I want. Okay, so if you downloaded the data and put it in the TMP data, you should be able to run this without having to download the data again. It's just a way so that you don't have to download manually the data. Okay, it's a purpose of robot disability to have the R code that downloads the data for you. It's better for reproducibility because then people can just run the code and it will download the data. Then you don't have to write download the data there at this link and put it in some folder or whatever. You just have the code that does it for you. The next time you do it, it doesn't download the data, it's already there. So it's efficient. Then it's a zip file, you need to unzip it. Yes, unzip. You can, normally you can, if you want to copy, you can use that. It works as well. It should work. Okay, unzip the files. It's already there, so it doesn't unzip them. So do you all have the data? Because if you don't, then it will be a problem. So again, Plink, you can download Plink from R with this function that I provide. And if it's already there, it doesn't download it anymore. It just see that it's there. So at some point, maybe you want to download again because if you do that for like 2 years, then you would end up with a 2-year-old version of Plink. So I think at some point you can just write overwrite equals true. It will download it again. The connection is Yeah, Amplex for 6 megabytes. It's not very good. Yeah, for some reason the data is not ordered and by chromosome and position. This data. It should never be the case. I don't know why this data is like this, but well, they provided like this. But it causes some error when you run Plink. So what you need to do is just run this, and it will make it just make it sorted. So I'm just calling Plink here directly from R, right, with the system call. Okay, so let's work with this data now. Okay, so to perform some quality control, we can use this function PlinkQC. We provide the Plink path, and then the prefix, the bedbeam files. Yes, it's already there. QC sorted. I can delete this. Okay, so here it's just running Plink. So you can see the Plink log. It tells you the options in effect, the amount of memory that is used. You can see the number of variants and the number of individuals. You can see that none of the individuals were removed based on this threshold on missing values. So this remove individuals with more than 10% of missing values. So there is no individual with more than 10% of missing values. So it doesn't remove any. It tells you that only one core is used. So apparently you can use many cores. So in Plink, I think it's threads. So I don't know why I don't have an n-core parameter. Maybe I do. Maybe it was because before it was not parallelized. So let's try it like that. Yeah. So does anyone remember the name of the parameter for running in parallel in Plink? Yeah, I think don't have any parameter for running in parallel because it doesn't work with this function. But it should be very fast, so even running it sequentially is okay. You can see the jump adding rate, so you have 2.2% missing values basically. The number of variants that have been removed due to missing data. So the number of variants with more than 10% the default. So all the variants with more than 10% missing values are removed. You have a threshold on minor allele frequency, which is by default is like 1%. Some threshold on RD1 equilibrium. Yeah, be careful. So RD1 equilibrium is basically testing the SD actual genotype. The standard deviation is like 2p 1 minus p. So out of that, where p is the allele frequency, it should be normally should be about the same thing. The issue is when you have multi-ancestry data, the frequencies in each ancestry are not the same, and so this doesn't hold anymore. Yeah, so this is why I use a very stringent threshold, where the default is I use a very small p-value because of this problem. I don't know if there is a way to run this Hardy-Weinberg equilibrium test per ancestry in Plink. But just keep that in mind that if you have multi-ancestry data, basically it doesn't hold anymore. So you would remove many variants if you use something that is not too stringent. Yes, and by default, to make the new files, it just append QC underscore QC to the prefix that you have, but you can choose prefix out to be whatever you want, right? Okay. When you have data that is not in a bin file already, you can use this file type. So it just the parameter in Plink to say which format do you use as input. So the B file corresponds to the bin file. If you use map file, you can use file. If you use VCF, you can use VCF. And if you have a compressed VCF, you can use GWAS. Okay. And it will do the QC and the conversion to bin file at the same time. Okay, now that you have your Plink bed file with some QC done, you can read it as a bigsnp object to be used with the packages. So to do that, you can use snip read underscore read 2. Yeah, so you provide the bed file, the path to the bed file. Then you provide the path to the backing file, so remember the BK and RDS file, the prefix for that. So by default, you will just use the same as the bed file. Okay, the same name. So what you get from the bed bin fam is just a BK and RDS file as before. And if you need, you can provide some indices of the rows corresponding to the individuals and the indices of columns corresponding to the genetic variants. If you want to read only a subset from the bed files, you can do it also. And by default, it just read them all. And you can use some parallelism if you have to read some very large bed files to make it faster. And yeah, I just provide this NB cores function to try to detect the number of cores that you can use on your computer. Okay, I have 4 here. And what you get from this is not the actual data in R, it's the path to the RDS file. Okay. So you have the BK file, which is it's not very large, but it's quite large, storing the data, and this RDS file storing the objects. So what you need to do now is to use this snip underscore attach to get the object in R. So now that you've read the bed file into the bigsnp object, you need to do this only once, and each time you load your R session, what you need to do now is just use snip attach under this file. Okay, so you can write it directly like this if you want. GWAS. Okay. Now I can quickly look at the data. So as I said before, it's just a list of 3 things where you have the genotypes, which is just the FBM. So usually I do it like this. I call that G. It's my FBM I can see I have 1,401 individuals, the rows, and this number of columns, the genetic variants. And there are like two other things. You have the data frame. In the FAM element, you have a data frame with information on the individuals that is directly read from the FAM file. And then you have data frame with information on the genetic variants, which is directly read from the BIM file. Okay, so this is the BIM file, basically. Before it was the FAM file. The genetic data is just corresponding to the BED file. And you get everything in R. And then you can access, for example, first column. Yes. Any question on this preprocessing reading? So let's read also some extra information. So there is some extra information stored in the CSV file for the individuals. So you can read the CSV file. So what you get is just a data frame. And I want to add this information to the information I have in this FAM component. I can see that this ID should be the one I can use to match between the two. Yeah, so to add this new information, I can match these two IDs to get the order I need to access. So I match the ID in my genetic data, basically, to the IDs in this clinical data. And what it gives me is the order I need to access the elements. Basically, I think they are in the same, yeah. They are already in the same order, so I don't really need to do this, but yeah. So then I can access this clinical data in the order to get the exact same order as before. As my genetic data, the FAM. Right? And here I just make a quick check. I also can see that there's the sex information. So I just check that now the new data, the new order, if I access sex, is the same as the one from the genetic data, just to make sure that order is okay. And it's okay. Yeah, so now I just combine, so combine column concatenation, right? Column binding with this information. So I don't need the FAM ID sex because it's already in the other one. And then I get to the first values I had here, plus some other information. Another way to do it would be even easier way to do it. Okay, I will revert back to the first thing. How can I add the information to a data frame? I have two data frames. I want to combine them in one with all the information. Yes. I can use dplyr, the left join. So I want to add, it's called left join because it adds on the left data frame. It will add the information from the right data frame on the left data frame. and then I need to specify the columns that we use to join to the information in common. And I need to specify here one on the left and the one on the right, which is this one. Because it's not the same name, I need to provide both names, the one on the left, the first one, and the one on the right for the second one. And I think I can use sex as well. Yes. Okay, and when I do that, matches with both these columns, and just add the extra information from the data frame on the right to the data frame on the left so that I have all the information at the same place. So either you write this match, you change the order, and then you combine this, or you can just do it in one line with a left join. Okay. And the benefit also of the legend is that you can match on many columns at once. If you want to do that with match, you need to use vectors match, which is a generalization of match, basically, to match with many columns. Okay, so this is I've just added some information on the individuals. Then I can look quickly at the number of missing values. So for that, so I define my G. Usually I call this G, genotypes, the FBM. And then I can run B counts. It will just count the number of 0, 1, and 2 and NA per genetic variant. So I know that for the first genetic variant, I have like this number of zeros, ones, and twos, and this number of NAs. Okay. So it's a quick way to get the number of missing values per column. And then I can look at them. So you can see that no genetic variants have more than 140 missing values. It's because we had some threshold at 10%, and we had 1,400 people. Okay. And if I want to do a quick imputation, I can use this function, snip fast impute simple. I can impute by the mean. I can impute also by the mode, random. Yeah, okay, the mode and the median would be the same. No. So the mode is like the most frequent value. Mean 0 would be the mean but rounded. Mean 2 is the mean but rounded to decimal places because it's what we can store. And so if we look now at the counts, you can see the number of 0, 1s, and 2 are the same as before. And then the NA have been replaced. They have been replaced by uh, 0.1, which is the mean of so now you don't have any missing value anymore in G2. Okay, something So G2 is a new FBM. But actually, if you look again at the counts of G, there are some missing values in G. So G has some missing values, but G2 doesn't. They both use the same underlying data, so the binary BK file on disk. The difference is how they decode the data. The difference is here, the code that they use. So this value is coded as 0, 1, 2, and then all the other values are coded as you get missing values. But G2 is using this dosage. So here you have the dosage. And basically it's this value that is used for, is the mean for the first column, for example. So value number 18, but you can see that the value number 18 here is decoded as a missing value. Okay. So they have a different code here, decode the data. And what we need to do is to say, I want to use this new, this FBM with the new code. So I just put that here. Just replace the genotypes component with the new FBM. Okay. So now what I have, I have this genotypes with the code for the dosage. I have the FAM component with all the extra information here compared to before. But I need to store this in the RDS file so that next time I load the data from R, from the RDS and BK file, would be the same. Because if I run this again, if I run this again for now, with this bigsnp 0, and look at the FAM component, for example, I don't have the extra information. I didn't store it in the RDS file. So next time I read it from the RDS file, it's not there. The extra information on the FAM individuals, the new code for the FBM, it's not there. I need to save them. To do that, I can just use snip save. And then if I run this again, so next time in next R session, when I load this data from the RDS file again, now you can see that I have the extra information that is stored. And then if I look at the missing values, I don't have any missing values anymore. Okay, so now my data is ready to for analysis. I did some QC. Load it in, I converted it to my format and filled the missing values, and also added some extra information from an external CSV file on the individuals. Okay, so I have everything I need now in this RDS and BK file to work. Okay, so this afternoon we'll talk about the population structure. So I will explain a few things. We'll see some code, and then you have to write your own, like you have to rewrite the code somehow. You will see. Okay, so PCA is very important because you can get population structure. So if you run a principal component analysis, on some genotype matrix. The first pieces usually capture population structure. So usually you can see like a triangle with like Europeans, Asians, and Africans. And if you have only European data, usually you see a north-south gradient, and then for PC1, and then west-east gradient for PC2. So you can capture population structure, which is important to if you want to control for population structure in GWAS, for example, and other analysis. So actually, PCA can capture a lot of structure, different kind of structure. So we have population structure, what we want. You can capture LD. So if you have lots of correlation between variants, and for example, if you have long-range LD regions, so regions that are with lots of LD between all the variants, so sometimes you capture this in the PCA, and it's especially the case when you don't have much population structure. So for example, if you have only European data and not a very diverse population, you can quickly capture LD instead of population structure. So you have to be careful about that. You can capture relatedness. So if you have related people when you run PCA, you will see them cluster together in the later pieces, and we'll see in some plots. And then I think it's basically the three kinds of structure you should get, and then you have noise, the rest, which is basically just circles. So what we are really interested in is population structure. So population structure, yeah, it's the second main topic of my research work. After project card I will introduce tomorrow. A bit of the work I've done. So introduce an algorithm to compute PCA. So we're accounting for the LD problem. So usually when you run a PCA, you have to perform some first phase of pruning, where you remove variants, pairs of variants that are too correlated, and keep only one of them. Yeah, just I use clumping, which is basically the same. If you want to know the difference, you can look at this vignette. And also you have to remove long-range LD region. So this region of where you have like lots of variants that are highly correlated, where clumping or pruning is not enough to remove the LD structure, you also have to remove this long-range LD region. And what I did, I implemented an automatic detection and removal of this long-range LD region, because usually you have a list. For example, if you go to wiki, yes. There is a list of long-range LD regions that you can use and remove from your data when you compute the PCR. The issue with that is you can have more than this actually. So I just decided to have an automatic way to detect and remove these long-range LD regions, and implemented that. In this paper, I improved some algorithm called PCAdapt to detect variants associated with population structure. So it's basically a GWAS for population structure. And then, as I said before, I extended bigsnpr to also run directly on the pling bed file. So all these bed underscore, the function starting with bed underscore are from that and can be run directly on bed files. You can have a few missing values, a small percentage of missing values, so that you can have missing values there. And investigate the best practice for PCA. So it's actually what we use, the bed function in this example, and then you will have to rewrite the code using the snip underscore function. Yeah. And then I worked a bit also on detecting like ancestry inference and grouping individuals into an homogeneous ancestry group, and inferring ancestry from a summary statistic from L frequencies. And so you could do all that with the packages. Okay, so there is an example here. There is another tutorial with even more detail, I think, in this vignette that you can have a look at later. So I will just explain the few steps, like the many steps. Okay, so let's load the data. So I will just start again with a clean session. So usually in my code, I have a R script for pre-processing the data, getting the data in the format I need. And then I have a different script for analyzing the data. And each time I start with a clean R session. So each time I load the package I need. When you load bigsnpr, it automatically loads bigstat as well. So you don't need both to load both. It's already done. So here we'll work on the bed file that we make, the QC one. And as I said, you will have to do it again, but on the bigsnp object instead, by using the same function, but for the different format. Okay, so I have 4 cores here. I want to use Pling2 to run King, and I can run King as before. So here I use make bed equals false. So I don't want to make a new bed by removing the individuals. I just want to report all the pairs of related people. So if I run this, you can see I have this threshold. I want to make this King table. I use parallelism in Pling. Yes. And what I get is a data frame of 51 observations, so the 51 pairs of related people. And then I can look at the histogram. So I look at the histogram of the log 2. So here, if you remember from before, so 2 to the power -4 is like third relatives. You can use this threshold to the power of -0.5, or you can use also to the power of -3.5 if you want to keep cousins, but remove all the other pairs of individuals that are related. So here you have very small values for the kinship, which means that there are not really many related people, and the people that are related are maybe just cousins or it's not very related people. So here it's not really an issue. So we won't remove any individuals for now. If you want to look at the like an example where I remove some individuals and then I have to project them again, it's in this vignette. Yeah. Something, just a note, LD pruning is not recommended with King. So just run it on the full bed file. But sometimes it may be useful to filter out some variants that are highly associated with population structure. So I read that from the UK Biobank paper, where they did that. They had to remove some variants that are too associated to population structure. I did that for the eyesight data when I computed the related people. And you can see the code for doing this that I use for the eyesight data here. I tried on this example, this data, to remove the variants that are too associated with population structure. It didn't change anything. So yeah, I don't know if it's a large problem or not, if it's really needed, or if it's only needed when you really have a diverse population. Like in the UK Biobank, you have people from everywhere in the world. So they are from UK, but originally their parents maybe from different countries, even them can be from different countries. They were born like in all parts of the world. So it's a very diverse data set. Yeah, as you will see later, it's mostly European people. So
not recommended.
It's
Is it something mathematical?
it's what they write in their recommendation, and I think they do some filtering themselves. When you look at the scan for rare variants, okay, and then the initial scan, maybe it's rare variants. I think that there are some ways to filter like variants that are a bit weird, but they don't do any filtering on the LD, and they say explicitly that you shouldn't do that. So yeah, because I think they recommend to do that when you compute the GRMs, maybe. Yeah. Yeah, but it's just for king. When you run king, you don't have to do LD pruning. But when you run the PCA, you have to do it. Okay, so relatedness is not a major issue for this data. So let's compute the pieces. So all the code that follows will directly work with the bed file and the bed functions. But everything can be run on the bigsnp object instead. And it's what you will have to do at the end. Okay, so we need the bed object. So what you need first is to use this bed function and provide the path to the bed file, the QC one with the underscore QC. And this will just memory map the bed file and read the beam and fam files to get data frames. So when we look at this object, which is now a bed object, I assume I call it, yeah, a bed object anyway. If we look at it, we have the external pointer, which is just the memory mapping. And we have the fam and map. As before, we have fam and map to get you information on individuals and the genetic variants. And then to help you, if you need that, you have the bed file, the prefix, the beam file, fam file, and so on. That you can access, for example, I can just say $prefix and then get the prefix of the bed file. Okay. Okay, so it's the same as the bigsnp object, but instead of converting to a FBM, it directly memory mapped the bed file as if it was a matrix, but it can read directly from the bed file. I don't think I've implemented the accessor like this. Yeah. If you really need this, you can use bed matrix bed. Yes, bed matrix. It's another package to memory map bed files. And then I think then you can use it's to provide the accessor, the matrix accessor to the bed file directly. So it's also memory mapping the bed file, and then you can have you can use the standard accessors from R. Yeah, I guess I should implement this. It may be useful. Yeah. Don't I have something like this? Read. Yes. Yeah, I have this function, internal function. Okay. Okay, now that we have the bed file, the bed object, we can run this function bed auto SVD. So the auto SVD is what I talked about earlier. It does the clumping step for you. It does the detection and removal of LD regions, long-range LD regions for you, so that you don't have to do it. It's already done automatically. So let's try that. So here I've wrapped this call. So the function is just this, right? The call. I've wrapped it with this run once save run. So this will run the code once, store the results in this RDS file, and then next time I run it, it will just read from the stored file. Okay, so it's just a way to cache the results in some way. So that when you have long runs, you can just store the results, and the next time you rerun, you want to rerun your script, then if you don't expect the result to change, then you can directly read the save object. Right? You don't have to save yourself, and so here it's already computed, so I can just run this, and I have the object. But let's run it together. So if you run this, the first time it will run the code. Here I'm running it like this because for me it's already run. It's already saved in this file. Okay, so it will take a bit of time. For me, it takes a bit more than 2 minutes. So depending on your computer and whether you are plugged or not, you should be plugged if you want it to be faster. It can take a few minutes. So just to explain for the first things, so you have a first phase of clumping, like pruning. It's basically similar, where you keep basically this number of variants. Then there is a second step where I remove the very low frequency variants. Okay, so here there is no very low frequency variant because we performed some QC before we spin. And then there are many iterations where it computes the SVD. So SVD stands for singular decomposition. It's the same as PCA. It's two names for the same thing, basically. And then it automatically detects outlier variants, which is the variants that may be associated with LD and not population structure. So it detects them, and it can also say that some of these variants are like contiguous variants that form two long-range LD regions. I just detect them and say, oh, it has detected like two long-range LD regions. It just removes the variants, the 309 variants from the analysis and perform again the PCA. So he has to perform the PCA multiple times, basically. For the second time, you have 19 outliers. The third time 3. Then 15. I think it stops automatically after 5 iterations if it still detects outlier variants. So here in iteration number 5, it doesn't detect any outlier variant anymore, so it stops. And basically, from the analysis, so from the clumping step, I get this number of variants, and then I remove these variants, these variants, these variants, and these variants. So just a few more to get this. Okay, so it's the objects, the SVD objects, where you have the singular values, you have the left singular vectors, the right singular vectors. This is the center and scale. So this is when you run PCA, usually you scale your genotypes, so you center them and scale them by the standard deviation. So it just reports the center and scale that was used. And you can access the attributes. So you can access attributes of the objects and then subset. So this is the list. So this is the vector of indices, the variants that were kept. So as I said before, you keep only this one from the clumping step. Then you remove a few from the LD regions detection. So in the end, you keep only this number of variants. This will give you the indices of these variants that are kept in the analysis. Then you can see the long-range LD regions that were detected. So LD, LDR, which comes from long-range LD region. Yeah. Okay, so this should handle the LD problem, this auto SVD, by just doing some clumping plus removing of long-range LD region automatically. Then we can check. We can look at the some plots. So here it's the scree plots, so the plot of singular values. Actually, there is a log. I use a log scale usually here to better see the difference. Zeynep, do you see something very dissimilar here for the plots?
Something, yes.
But is it similar? Okay, yeah. So this is the scree plot. Then you can look at the PC scores, which what you see usually in papers. So here I say I want the scores from 1 to 12. And this is just a coefficient to make everything a bit smaller, the text, because you have 6 figures instead of just 1, so you need the text to be a bit smaller. So I just say I want to be a 50% smaller. Want to be 50% of the initial size. And then this is what you get. Okay. So I guess this is population structure. This I'm not sure. This three.
This ED, that's the singular value.
Singular value decomposition, yeah. Singular value decomposition, yeah. It's the same as PCI. It's the same name.
Okay.
It's the same. Yeah. Okay, and you see this these 2 dots here and these 2 dots here. I would say it's related people. It's usually what you get when you have related people. They appear like this in later pieces. Okay, so based on these 2 plots, here, do you know the rule to choose the number of pieces? Like the rule? It's when you have something flat here, you know, from 7 to 12, then you choose the one before, so from 1 to 6. Okay? So this gives me a rough idea of what the number of pieces I should use, and then I kind of confirm with the PC scores. And then here, I use 1 to 6, because here it's basically just just some circle here. So you don't really have any structure anymore. So yeah, I would use 6 pieces in this case. If you run a GWAS and use maybe 12, I'm not sure it would change much anyway. So you can use. So the problem, if you use too many and it's just noise, you kind of lose some power, a bit of power in your GWAS. But yeah, it's not much. I mean, it's basically the same as having, if you use 6 more pieces, it's the same as having 6 less people in your data, which is, I mean, not that much. So.
Just one question. If you change the number of pieces, let's say you keep increasing the number, and if it keeps changing the significance, it comes out from your analysis. Does it tell anything or suggest that
you mean from the GWAS?
Yes.
Yeah, that's a bit worrying. So you should be careful about LD, not capturing LD. I will talk about it in just after. Because if you capture some LD, what you capture is basically one region. Yeah, maybe I can. it would be better if I can show you the peaks. Okay, let me do something, and I will explain again this LD problem. So you need to make sure that there is no LD structure capture in the PCA. So what you need to look at is the loadings. Loadings are the weights of each variant for each PC. So you can plot them like this. So here it's like, because there are many variants. If I plot every dot, it would take too much time. Right? I have like 400,000 variants. If I plot them 6 times, it would be like it would take 10 minutes to render the plot. So instead, I use XBeans. It's like a 2-dimension histogram somehow, density plot, where the color is the counts that are in each. So you should get something like this, where you have basically the effects of each variant are spread over the whole genome. And if you have some LD problem, you will see some peak. And maybe I can show you by just computing.
And then if the time switch,
Okay.
So the and then
okay. So it was a typing errors. Yeah, but I'm already talking about peaks in the sense that many variants close to each other all have a large effects, but maybe 100 of them are.
So it was, yeah. So the problem was response after removing time.
Okay. Do we have the bed random SVD? Yes. Publish bed. So here I'm running some SVD on the whole data without doing any clumping and any removing of long-range LD regions. So normally it should be I don't know 30 seconds, because we don't have. So I'm doing only one step basically, but on the full data. So instead of having like 100,000 variants, I have like the 400,000 from the initial data. And why random? It's because SVD or PCA can be very computationally demanding. So there are some ways to make it much faster and to make it linear with both dimensions, meaning if you increase the size by 2, it will increase the computation time by 2 and not by more. Like for example, there are some algorithms where it's quadratic with the dimension. So if you multiply by 2, you multiply the computation time by 4. And if you multiply by 10, it's multiplied by 100. So it gets it takes a lot of time very quickly. So this one makes it just much faster. Okay. Let's look at the loadings. Yeah. So you see, so here it's a small peak, but here you can see it very well on PC4. So PC4 is basically capturing the LD structure in this region. So for PC4, all the variants in this region will have a large effect, which means that if you include this PC4 in a GWAS as a covariate, it will bias all the effects from this variant, because this is basically correlated with the variant. So you will bias the effect size for all the variants in this region in your GWAS if you include PC4. So you should be careful about these peaks. If you get some, usually you shouldn't get any if you use auto SVD. But if you don't do any filter, like enough filtering on the LD, then you would get this and it could bias your analysis. Okay. And maybe we can look at it. If I look at the scores and then 3 and 4. Yeah, the scores. Yes. So do you see it? Do you see PC4? What is it? Which max V4 squared. Okay, this is the variant with the highest loading for PC4. Okay. I do it like this. Color. I will color by. I need to access the genotype, the genotype. Okay, so here I have the genotype for this variant that has the highest loading. So if I color by this, yeah, S factor would be better. Okay, so PC4 is basically one variant, which is, it's useless. And when you have this variant in the GWAS, it will bias completely the effect size of this variant. So yeah, you should be careful with LD. But normally using auto SVD should be fine. Does it answer your question? Yeah. Okay, let's. So yeah, it's doing the SVD without any filtering on LD. I use all the variants. Then I looked at the loadings. The loadings, it's the effects of each variant in the pieces. Yeah, we just. And in this PC4, I can see this peak, right? So all the variants from this small region, like small in the plot, but actually large on the genome, they all have a large effect because basically you're capturing the correlation within this region. So I took the variance with the highest loading, which is around like 200,000. Okay, just before. I accessed the genotype values for this variant and just plotted C3 and 4 coloring by this the values in this genotype, particular genotype. And you can see that basically you're capturing this, which is not what you want when you run a PCR for genetic data. Okay, so before we had no peaks, which is good. This is a bit weird. This PC4 and 5. You don't usually see pattern like this. It's more like this, spread around 0. Here you have like many negative values. Yeah. So I'm not sure what's going on with this too. If it's some genotyping errors or I don't know. Okay, now that you have the pieces, you can do some more things. And for example, if you expect individuals to come from one population, for example, in ISAC, you expect people to come mostly from Denmark or around Denmark. But there are people from other ancestries as well in ISAC. But because most of the population is from most of the data set is from one population, then you can easily find these homogeneous people by doing some distance on the PCs. So to get the PCs, you can use predict. So when you have this SVD, you have U, D, and V. The PCs is just U times D. Okay. The left singular vectors, the singular values, you just multiply them and you get the PCs. If you want, you can just use predict here to get the PCs. So here I have the 12 pieces, yeah. But then I can compute the log distance based on the pieces. So I think this distance shouldn't care too much about how many pieces you use because the letter ones have a smaller singular values, so they don't contribute. They contribute less to the. But we can check. So if I check LDist and LDist2, and I plot one versus the other. So you could use only 6 pieces here, but just subsetting. And if we look at the histogram, so you can see you have the small distance here, the large distance here, and you need to pick some threshold where you split and say it's not homogeneous anymore. So basically what I do is I just look at it's like basically normally distributed here. And just stop when it's not like so here I would choose like, for example, 4.5 or 5 as a threshold and say, yeah, but this data is not homogeneous in the sense that it includes many people from different European ancestry. So by doing that, you would keep many people from different European ancestries, which is homogeneous, but not that homogeneous. When I'm talking about homogeneous people, I would say it's more like people from the same country or country around this. Yes, and we can look at the previous plot by coloring by this distance. Okay, so this I'm just sourcing some code, just a function plot grid 2 to make it easy to make many plots. So here I'm just plotting the PC score as before. I'm just coloring by the dislog distance. So you can see. So basically, what you remove is the people from here. So as I said, it's not really an homogeneous population here. Okay, an homogeneous population would be you have a huge cluster, for example, it should be around 0 normally. You have a huge cluster around 0. Then you have two tails. Like usually it's like, I don't know, people from European ancestry and people from other ancestry. And you get this, if you have many people from European ancestry, you get this huge cluster around 0. Then there are other people like Asians, for example, and Africans here. And but here you have people a bit from everywhere, so it's not really homogeneous. So maybe you shouldn't use this log distance. But for like data like ISAC, where 80% of ISAC at least is like Danish people, and they're all Danish, but I mean, coming from Denmark originally, their parents, their grandparents, and so on. And the UKB, it's the same. It's maybe 80% at least are from the UK originally. It works very well. So now it would be nice if we could get a sense of the ancestry of these individuals. So to do that, you can use this code, which is a bit more complicated, but I will try to explain it. So basically what I did in UKB, you have people, as I said, you have people that were born in many different countries. And I use them to get some reference population for many diverse ancestries. I think I made like 21 groups, different groups from everywhere in the world, like almost everywhere. And I use that to make a reference, some kind of reference panel to infer ancestry in other datasets. So it was made like to infer ancestry from allele frequencies. So if you have allele frequency from a GWAS summary static, for example, you can use a function called this one, SNP ancestry summary. Where you provide the frequencies, the allele frequencies. You provide the frequencies from a reference panel that I provide to you to download. Some projections, so I project this on some PCA space to get more power. Then you need a correction for the PCA because of the overfitting of the PCA. So these three are provided to you. It's just you need to download them, and then you just provide the frequencies, the allele frequencies from your data, and it will give you an estimate of each ancestry proportion in the proportion of each ancestry in the summary statistic. Okay. And actually, when I did that, I realized that I could do it for individual level data as well. Meaning I could get the genotype of one individual and replace, so instead of providing the frequencies here, I could just provide the genotype of one individual divided by 2. And it will still work. So I could get the ancestry proportion for individual level data. Okay. So it's not implemented in a function. You have to, it's not implemented in this function. Maybe I should do it. Yeah. Maybe I should implement a function so that it's easier to do. But basically what we'll do is write the code that is in this function to do that on individual level data. So for each individual in our data, we want to estimate the ancestry proportion, or we want to group them in some cluster, some ancestry cluster. Okay, so as I said, we need all these three things. Okay, I can just like. So these are the frequencies, the allele frequencies for 6 million variants across 21 ancestry groups. Actually, the real one that you should use in real analysis is this one, but it's much larger. So for the tutorial here, just filter to have the same variant as in the data, 400,000 or 500,000, to make it smaller so that you can download it faster. So it's just a subset. Here, what we'll use is just a subset, the variants that are provided in this, that are in common with the data that we have. So you should already have downloaded it. So it should be just a matter of reading the text file. So it's a CSV.gz, a compressed CSV file. And we can see what is it. What you get is the data frame. The first 5 columns are information on the variant, so chromosome position alleles, and the RSID. And then you have the frequency of these variants in many ancestry groups. Okay, which is the allele frequency in many ancestry groups. Then you have the projection. So the projection is just the PC loadings. For each variant, again, the same variant the effects for each PC, the PC loading for the PC1 to PC16, which is the number of PCs that I choose in this data. And here it's the correction you need to apply for each PC. So if you read my paper on this one, no, not this one. You will learn that when you project PCs onto a new data set, there is some shrinkage. Basically, when you train a PCA on some data, you can have overfit. And when you project this PC space, like other individuals into this PC space, there will be shrinks towards 0. So you need to apply some correction so that it's not shrink anymore. And this correction is this one. You can see that, for example, for the first 4 PCs, you don't need any correction. But then if you look at PC16, then you start to need some larger correction. And the less number of individuals, the smaller the number of individuals you use in the PCA, the larger the correction should be. So for example, if you use the 1000 genome to compute your PCA and project that for some other individual in the PCA, the correction will be bad very quickly that you need to apply.
These numbers are absolutely not realistic.
So this is the one that you should use for this projection. But if you do another, if you run another PCA on some other data, you should use a different projection, different correction. But there are some functions. If you need to do that projects, I talk about that in the paper I talked about, and yeah, there is a function to do it. And in this function, you need to provide both the file for the reference population where you will train the PCA, and the bed file for the new population you want to project.
That's our choice. That we are analyzing.
So this would be, for example, the 1000 genome if you want to use 1000 genome. And the new would be the one that you're analyzing, yeah. And when it will compute the PCA, it will also compute the correction that needs to be applied, and apply that when it projects the new individual. So now I don't use the 1000 genome anymore because the 1000 genome is very, it doesn't include all the different ancestries. So basically you have European people, you have East Asian people, maybe you have South Asians, I don't remember. And in Africa, it's mostly people from West and South Africa. So you don't have any North and East Africa. You don't have any Middle Easterns. You don't have, yeah, it's missing a lot of population. So I tried, it's what I tried to do is make a more diverse reference panel with the UKB. Yeah, like this. Okay. Okay, now that you have this, you need to match the variants. So I provide some frequencies and loadings for some variants, but you need to match them with the data that you have to use the same set of variants. So to do that, so we take the map, which is the information on the variants in our genetic data. Here I just transmit. So transmit is a dplyr function. It's just a way to rename. I could have used rename, yeah. Just to rename. So I will say now it's called Chrome, just like this. This will be called pause. This will be A1 and A0. Okay, to get the same names as in my other data here, are required for the SNP patch. I can use this function snip match from the package to match between two data sets. So it will match by chromosome, alleles, and either position or SID. So by default is position. But if you have like a data set with position from two genome builds, maybe you want to use the SIDs instead. And normally it will detect the strand flips and reverse of the reference allele. So for example, if you have C and G in one data set and G and C in the other data set, you will know that it has to reverse to be able to match them. Okay, so if I run this, yeah, we'll get, so this is the data that was used to match between the two sets of variants. The beta here is -1 is if the alleles had to be reverse switch, and it's +1 if it didn't have to. And this gives you the ID in the sumstat, the first data frame, and this will give you the IDs in the second data frame. Okay, if you need to access again from the first and the second data frame, you have the IDs corresponding to each variant that was in common between the two data frames. Okay, so in common here I have a bit more than 300,000, and at the beginning I had like 400,000, but in common I have only 300,000. Okay. So reverse is if you have to switch between 0 and A1. So if you have if you have GA and the other dataset you have AG, it has to switch. You have to switch both alleles to be able to match. And the strand thing is basically an A can be a T and C can be a G. So you have this as well that you need to take care of. No, you're reversing the alleles because flipping the strand doesn't change the direction of the effects. It's switching the alleles that change the direction of the effects. Yeah, maybe I should really make this as a function because it's maybe a bit complicated to code. I mean, you just have to copy paste, but yeah. Okay, if I want, I can do more filtering on the missing values. I'm not sure it's really needed. So here with bedcounts, and if I access if with bedcounts, you remember, yeah, I don't want to print that. Give you the number of 0, 1, and 2, and NA. So I can get the number of NA, and the ones that are less than 5% of the number of integers. And give me the indices that pass this quality control. And then I need to project the individuals. Okay, so the initial projection, with the PC loadings, you remember first 5 were like it was some information on the variants, and then I got the PCs. So I'm just removing the first 5 columns because it's just information. And here I access only the indices in common that I match here. So here it's just to access a subset. Let's do it like this. Okay, it's just to access a subset of the loadings that I want to use, the one I want to use. And then I need to project all individuals. So here it's what I need to do I need to take my object bed, so it would be the G2. Multiply by one column of this projection matrix, the loading. I need to apply this correction. I need to divide by 2 because this algorithm was designed for, like the reference was designed for allele frequencies and not genotypes. So you need to divide by 2 to get something on the same scale as the allele frequencies. Okay, so you compute the product between your genotype and the PC loading, and you do this for each PC loading. Okay, because for the bed file, I don't have a function to compute directly the product with a matrix. I have only with a vector. So you need to do it for each PC one by one, the matrix product. So you need to do G2 times V1, G2 times G2, G2 until G2 V16 number of pieces. And then you need to apply some centering and scaling because we've seen that the variants were reversed, like the alleles were reversed sometimes. So when it's the case, instead of using G, you need to use 2 minus G. You need to, a 0 needs to be a 2 and a 2 needs to be a 0 when you switch the alleles. So you can code this by just using this center and this scale. So if you do that, you get the projected correction where I don't have it. This one. Okay, and now you get all the individuals projected to all the pieces. Okay, and now yeah. Okay, so these are the frequencies, the reference frequencies that okay, for each variant, I get the allele frequencies in each of the ancestry groups. And I will use them as the centers in my PCA. Now what I need to do is just compute the distance between all my individuals to each of the center, corresponding to the center of one population. So this gives me for each individual distance, the center corresponding to each population. So you can see that the first one is very far away from in the PC space, but then are close to Europe. Then what I can do is just pick the minimum distance and assign this individual to the group corresponding to the minimum distance. But I have a threshold. So if the minimum distance is larger than some threshold, I just say that it doesn't belong to any group. Okay. So you have this threshold here. So I take the minimum distance. But if this minimum distance is larger than some threshold, then I get a missing value. Otherwise, I get the group corresponding to the minimum distance. Okay, so the first individual is clustered to Italy. Second is clustered to European Northwest and so on. And if I look at a table of all this, we can see that most people are from Europe. Okay, so it's a way to infer ancestry from your data for each individual. And if we plot again the PC scores coloring by this, it's what we get. So actually PC1, 2, and 3 show population structure, but I'm still not sure what PC4, 5, and 6 are. What is it? Because it doesn't seem to separate any population structure. So I just don't know what this and this and this, what is it? Yeah, if you can find the answer to this question. Okay, let's have a break. And then you'll need to adapt. So from here, starting from here, we use only the bed file. But you remember that from this bed file, we made the bigsnp objects. So the goal would be to use the bigsnp objects instead of the bed file. And instead of the bed underscore function, use this corresponding snip underscore function and try to rerun everything by switching to the bigsnp objects. So about yesterday, so we've seen the population structure, ancestry inference. I will try to make this as a function for the ancestry inference so that it's a bit easier to use, so that you don't have to use this code to get the ancestry inference. So I will try to make a function out of it. So if you use some function and look at the documentation and don't understand something in the documentation, for example, don't hesitate to tell me so that I can improve the documentation and make it clearer. Okay, so it's nice to get some feedback from other people, right? Yes. So let's talk quickly about the GWAS. So it's very easy because you have two functions. One that does linear regression. So when you have a continuous phenotype, and one that does logistic regression when you have a binary phenotype, like a case control status, for example. Okay. The linear regression is very, very fast. And the logistic regression is a bit slower. We'll see. Okay. And as I said yesterday, it's just a GWAS is just taking each column of your genotype matrix one by one and testing for an association with some phenotype. You could want to do that for other types of data, like other omics data or whatever. So this is not really specific to genetic data in some sense. So this is why it's in the bigstat-R package and not in bigsnpr. Okay.
So it says that's by
Yes, univariate means that one variable at a time, but it does it for all it's like a loop over all the variables, but one by one. Okay, we just use the data that we've made before. Okay, so loading the package, loading the data. So we store the result of the SVD, the PCA. So I'm just loading this as well. You can just use predict to get the PC scores from this object. Okay, you remember. So you remember also that we had some information on the individuals. Okay, so the first 6 variables were from the fun file, and then we combine that with some external information from some CSV file. So for all individuals, we have this information. And the question is which of these variables we want to use as covariates in the GWAS. So what we want to use some pieces like population structure. So we choose 6 yesterday. So we'll use that as covariates. We can use sex as covariates. This will be our binary phenotype. We can also use age if we want as covariates. Sometimes people use age squared as a covariate. Yeah. Okay, affection is not maybe the one that we should use. We should use CAD, which is the binary phenotype. I'm not sure what is affection then. Anyway, and then you have information on HDL cholesterol, LDL cholesterol, and triglycerides level. So should we use that as covariate in the GWAS? Okay, it was shown that you should not have covariates that are heritable covariates, because it can bias your results in the GWAS. Okay, so you can look at this paper if you want to know more about that. We won't use these 3 other variables covariate in the GWAS because of this reason. So we'll just use sex, age, the first 6 species. Okay, so we just do that cover, and then we have 8 variables to use as covariates.
Sorry, I have a question. So I asked this to be honest, but isn't sex also heritable?
If you do a GWAS of sex, you shouldn't get any heat or any irritability, right? Yeah. But you can ask Bjarne about this because he's a author. Okay, so we have the covariates. What we need as well is the genotype matrix, we call it G. And we need the phenotype, and I usually call it Y. Okay, so you have the covariates, the genotype matrix, and the phenotype. The only thing I need now is to make sure I don't have any missing values in the phenotype or in the covariates. So here I'm just checking that there is no missing value in the phenotype. And here there is no missing value in the covariates. So this complete case just tells you if one row of the data frame or a matrix has any missing value or not. So here it's all true. So it means that there is no missing value in these first rows, and actually they are all true. So it means that there is no missing value at all in the covariates. So it's fine. But if you look at the phenotype, okay, there are no missing value in the phenotype as well. So actually, you don't need this, but okay, in some other code, you might need this. So this should give you all the indices. Okay. So as I said before, if we want to perform the analysis on a subset of the data, so here we talk about a subset of the individuals, but we could also want to perform the GWAS in only a subset of the variants. We won't make a copy of the data corresponding to this subset. We'll just use the parameters that are available in the function that are often called like in row or in trend for the individuals, and in call for the variables, the genetic variants. So we have this for example, in a big univlog rec, where you can provide, for example, in train, and just provide this vector of indices that you want to use. Okay. So this enables to basically just use a subset of G, but without making an actual copy of the data. It will just access the subset corresponding to these indices. So here we subset the phenotype corresponding to these indices and also the covariates that correspond to these indices. Okay. You can run it in parallel, and because it takes a bit of time, I'm just saving the results as before with save run in the run once package, so that the first time it will run the code and store the results in this RDS file, and the second time you run that, it will just get the result directly from the RDS file. Okay, so let's do it. So I will remove it so that I can do it again. So I'm not sure where it is. Okay. It's a bit weird because I have like, I should have 4 cores, but there are 2 that are listed under RStudio and 2 that are listed outside. I don't know why, but there are 4 cores that are working in parallel right now. To this GWAS. So it takes about 2 minutes for my on my laptop. I don't know how much time it takes for you. You should have a newer computer than mine, so it should be faster. Yeah, because so this is to subset G, but you also need to subset the phenotype and subset the covariate, right? But this is just a vector, right? And this is just a small matrix with 8. Yeah, but so this is just a vector, right? So it's very small. And this is just a matrix with 8 variables. So it's also very small. So it doesn't matter that you make a copy of that because it's very, very small objects. How many cores do you have? Yeah, I should ask for a new computer. Okay, so it takes a bit more than 2 minutes. And if you try to run a linear regression instead of a logistic regression, so I'm just replacing lin by log by lin, right? It takes like 2 seconds. And actually, usually, except for very large effects, the linear and logistic regression should give you similar p-values. So if you just need something quick, then you can just run a linear regression on the case control status. We can check. So if you run predict on this object, what you get is the log p. You get the log p-values, log 10 p-values. You can say log 10 equals false to get the p-values. But let's get the log p-values. So I'm just quickly showing you that the p-values should be about the sum. It will take a bit of time to plot because I'm trying to plot 500,000 points, which is basically you should never. I mean, if you want the plot to render quickly, you should never plot more than 50,000 points. Okay. So it's you get similar p-values between linear and logistic regression. So if you just need to quickly check some hits, you can just run linear regression if you want. Okay, so you have some plot methods for these objects. So if you just plot GWAS, what you get is the histogram of the p-values. Okay, so it's well calibrated. You can make a Manhattan plot. So you need to provide the chromosome and positions here. And here, with this parameter, I can say that I want to plot only the 50,000 points that are the highest, with the most significant, so that the plot is faster to render. Okay, instead of plotting the 500,000 points, I just plot 50,000, but the most significant one, and then I get the Manhattan plot. Okay, we don't get anything significant here because the data is small. We don't have enough sample size to get some hits almost. Okay, and this is the genome-wide significance threshold that people usually use. Okay, I think you can also, don't do it often, but you can also do a QQ plot. And what I usually do, okay, so the QQ plot where you get the expected minus stack 10 p-value under the null versus the observed one. And I'm just using this xlim to only show the value from 1 because this value we don't care. From 0 to 1 we don't care, and there are many values. So it's again a way to just make the plot faster by having less number of points in this plot. So very well calibrated.
Yeah, ask you, why, is there any reason why you don't use this QQ plot? Because it's quite often.
Because so before people use the QQ plot to so you wanted a value that is not close to 1, right? Because otherwise you would say, oh, there is population structure that you didn't take care of or something like that. But the issue is that now that we have very large GWAS, you get deviation from the line just because you're capturing some true associations. And it's just because of the Polygenic architecture of the trait that you get that. So there was a paper, I don't remember, genomic control, polygenic architecture. Yeah, I guess this one. And basically, it's if you capture some signal in the GWAS, it's expected that you have a deviation from the line because it's the line is just what you expect under the null when there is no association at all. But if you have many associations because you have a lot of power to do it, to get this association, then you expect a deviation from the line. So this line doesn't really tell you anything useful. So this is why people use L-discore regression. But there are also issues with L-discore regression when you have also a lot of power. You get intercept that is larger than 1 as well. So yeah, people use this ratio of whatever, I don't remember. Some transformation of the LD score intercept now. Yeah, so this is why I don't really use this QQ plot anymore. Okay, and let's do the same now with some continuous phenotype. So let's take HDL instead. So again, we look at the missing values and then use only we use a linear regression and use only the indices corresponding to no missing value here. So this is the linear regression, so it's very fast. And then I can again look at the Manhattan plots. And again, I'm unlucky because it's not genome-wide significant. Okay, you should be maybe a bit careful when you see this, but no, you don't really see any peak, right? You should be suspicious with this hits. And if we compare to the one for CAD, you see usually you see this you see some peaks, right? Like here. Yes. Any question on this?
Why is it suspicious? It's only one.
Because you should get the other. So because of LD, like because there are other that are correlated with this one, they should appear in the peak because they are indirectly correlated with the phenotype because they are correlated with the other variants.
Right.
You have indirect. You have your T1 that is correlated with your phenotype, and T2 that is correlated with T1. So it's indirectly correlated with the phenotype, so it should appear in the.
There are no LD regions. So
yeah, there could be, but yeah. So I'm not saying this is wrong. Just saying you should check. Okay, when you see that. You can look, for example, if you have like imputed data, you should look at the frequency. If it's very low frequency, you should be a bit suspicious. You can look at the info score, the imputation accuracy. So if it's low, again, it's a bit suspicious. You can look at the frequency and compare to some other data sets. See if the frequency is very different, then it's something weird as well. Yeah. Yeah. So I'm using this. So to solve the logistic regression, I'm using this iteratively or weighted least square, and sometimes it doesn't converge. So when it's the case, I'm using the GLM function from R, which use a better algorithm, but which is slower. So here it's the case only for one of the column or just one test. So I just use the better algorithm, but it's slower. But because I'm using it for only one variant, then it's fine.
When are you using with extraction to calculate the values? One test?
You can get the test. GWAS. Yes. Okay, so for the logistic regression, it's just a z-score that you transform to p-value. But then for the linear regression, it's not the z-score, it's a t-score, but it's about the same. Where you provide the degree of freedom, but a t distribution with like a large sample size, it's almost as a normal distribution, so it's almost the same. Any other question?
And I have one, So you run the GWAS on the whole set of SNPs or on the relative?
No, on everything. So if you look at the dimension of the GWAS, so the GWAS here is just a data frame. Each row is one of the variables. You get the effect size and standard error of the effect size. You get the score corresponding to it's the Z score, which is just the estimate divided by the standard error. And you get, this number of rows, so one per, and for the linear regression, you get again the effect size, standard error, and the t-score this time. And here it's just the number of iteration that was used to solve so that the algorithm converge, the iteratively weighted least square. Okay, so here in the GWAS and GWAS2, I'm not storing the p-values just to save some space, but you can get, as I said, the p-values. So here you get the log10 p-values, and if you want the p-values, you just say log10 equals what, and then you get the p-values. And it's better to work with log10 p-values. Why is that?
Because you can have a low.
If you have a very, very significant variant, I think less than 10 to the power of minus 300 or something, then it will become 0 because of the numerical precision in the computers. So you should work with log10 p-values because then you can store any small p-value that you want. Or you shouldn't use p-values at all. It's another debate. Okay, and at the end, I provide some example codes. So here, for example, it's some code to run a GWAS in ISAC. Some example R scripts that is on genome decay. So on genome decay, you can use many nodes, right? You can parallelize your computation on many computers, basically. So I just provide an example how to do that. So basically what I do is I just split my data in like 30, for example, 30 blocks of columns, and just compute the GWAS for each block in a different node in parallel, and then just combine the results. So it's like the split apply combine strategy, but it's on different nodes, so that it's just parallelized over many computers, basically, in some sense. Okay, here I provide some, I had to compute GWAS for many phenotypes, like more than 200, on some large data, so more than, I don't remember, 7 million variants maybe. So in that case, what you need to do to make it faster is to perform the GWAS for all phenotypes on a chunk of columns. So instead of parallelizing over the phenotypes and say, oh, each node will do the GWAS for one phenotype for the whole data, what you should do is each node will take a chunk of columns and do the GWAS for all phenotypes. And so why should you do that? So your data is split in a chunk of columns. So when you access only this chunk, as I said the first day, when you use memory mapping, when you access, it stays in memory as long as you have enough memory to cache the data. So if you only use a chunk of column, then the first time it's split from this, but then the second time it's in memory, so it's very fast. You don't have to access from this anymore. So the first phenotype, for the first GWAS of the first phenotype, for the GWAS of the first phenotype, you would have to access on this, but then for the second, the third, and fourth, it would be already in memory, so it's very fast. So it's better to do the GWAS for all phenotype for this chunk on one node, and then this chunk will be on another node, and so on. It's better to do that than say, oh, I want each node to do just one phenotype, but for the full data, because you would each time access the full data from this. Yeah. So you can look at the code to see and to parallelize easily on many nodes on some Slurm architecture like genome decay. You can use this template for that. Yes. So it's yeah, just the GWAS. So just like the standard GWAS where you do everything one by one. Okay, let's move on to polygenic scores. So developing polygenic score methods is the main topic of my research work. So what is implemented in the packages? So you have efficient penalized regression, so penalized linear regression and penalized logistic regression. So when you want to train a linear model, a predictive model directly on the individual level data. So if you have your genotype matrix and some phenotype, like what you do in the GWAS, but instead of testing each variant one by one, you train a model using all variants at once. Okay, so it's a predictive model with the full data. If you have large individual level data, you can run this. And again, it's not very specific to genetic data. You could want to do that for other data stored as a matrix. So it's in a bigsnpr package and not bigsnpr. Then you have methods that are specific to genetic data because they use then GWAS summary statistics. So we've seen, for example, the effect size and standard error of the effect size is what I call the GWAS summary statistic. There are methods that can use only this information to build the predictive score, the polygenic scores. One of the standard method, one of the easiest method that you could use is called clumping and thresholding. I won't really explain what it is if you don't know, but it's one standard method that is often used. And in this method, there are actually many hyperparameters. So I provide an implementation that allows you to test many hyperparameters efficiently. And then I have another implementation on top that enables you, instead of choosing one of the C++ score that correspond to the best hyperparameter, you can stack them. It means that you can learn a linear combination of all the C++ scores to get a better predictive model. Okay, so you can do that. Then I have LDPred2, which is a new version of LDPred, which is actually one of the best polygenic score methods right now. And then I also re-implemented the lasso sum so that it uses the exact same input data as LDPred2. So if you have your code that already runs for LDPred2, it's just one more line of code to run lasso sum 2. So that you can test many different methods with the same code. And so it's not polygenic score anymore, but it's still with LDPred2. What I'm working on right now is to validate LDPred2 for inference. So if you want to estimate the irritability, if you want to estimate the probability, the proportion of causal variance, you can do that with LDPred2 as well. Okay, so you should check the other tutorial for LDPred2. But then I will show a bit of code how to run this for this data. Okay, so I open a new script. I restart my session to clean the environment. So again, I load the package, I load the data. I use the name G for the joint up matrix. I get the number of cores that I can use, or that I should use. And then I access the information on the genetic variant in this data. So what I will need here is the information on the chromosome, position, and allele. We've seen yesterday it will be used to match the variance between two data sets. We just need the information on chromosome, position, and alleles. Okay, and then I computed some GWAS for coronary artery disease in the UK Biobank, and store that in a CSV file. So it's basically what you could get as a GWAS summary statistic. So here, when I want to read some text file, usually what I do is use read lines to look at the first few lines of the text file. So here I can see that these are the variables that are in the data. I can see it's a CSV. So it's a comma separated. Okay, and then I can read this data into R as a data frame. So here, I can provide the variable I want to read from the first line. And then the call names is the variable names I want to rename them basically. So I could just read everything and then rename later, or I can just do it like this, but just renaming when I read the data. So I want the information on chromosome, but I want it to be called CHR. Position, then alleles, I need to call that A0 and A1, as I did before. The effect size, I need to call them beta. The standard error, the effect size, I need to call that beta SE. And then I can read also the frequency and info score. We'll see it will be useful for quality control. Okay, so I'm just reading this. You may have some issue with some package that is not installed. No, no one has an issue. Okay. Sometimes they tell you to install the package r.utils. Yeah, it's the package that is used to compress the CSV file. Okay. So this is because we have a compressed CSV file here, it needs to be uncompressed and then read. And to be uncompressed, you need this package. Okay. Yes. And also, we need the sample size. So if you have a continuous outcome, just provide the sample size. If you have a binary trait, you provide the effective sample size, which is just 4 divided by the inverse of the number of cases and the inverse of the number of controls. And here you just have to trust me that what I use is this number of cases and this number of controls in the UK Biobank. So usually this information is given in the papers where you got the GWAS summary statistic. Sometimes it's a bit hard to find, so it's yeah, it's annoying. Yeah. So to run LDPRED2, we recommend to use a set of variants that is that are about 1 million variants called the AppMap3 variant. I extended this set of variants to include a bit more variants. there are like 1.4 million. And I call that the AppMap 3 Plus. This gives you a good coverage of the genome without having some set of variants that is too large, because these methods can be computationally demanding if you have too many variants. So if you try to run them on like 5 million variants, it will require some large memory, for example. So just some compromise between the two. Using this set of variants usually work very well. If you use a summary statistic from European individuals, I already provide the LD reference. So the LD is just a correlation between the variants. So what you need to run a Polygenic method that is based on summary statistic, you need the GWAS summary statistic, effect size, standard error, effect size, and sample size. And you need some estimates of the correlation between the variants, the LD. And I just provide some pre-computed LD to be used with this set of variants. Okay, so you should use that. If you have imputed data, you can get some other information in the other tutorial I took about. Here, for this small tutorial, we'll just compute the LD from the data we have here. So from the 1,400 people. Just note that usually I would say you need more than 2,000 to get some good estimate of LD. But just for this small tutorial, we just use the data that we have here. Okay, so we have the genetic data. So we have the information on the variants in this genetic data. We have the summary statistic with also some information on genetic variants. So now we need to match between these two data sets. So as we did yesterday, we can use the snip match function. Okay, so this is the number of variants I have in the data. And then these are the number of variants that are a match between these two. Okay, here I just use this option to return the information. So if I just use this, I get the information whether it was flipped or whether it was reversed to be able to match. It's just because when I use the frequency, if you reverse the allele, if you switch the two alleles, then you need to switch the frequency. You need to use 1 minus the frequency. Yeah, so I'm just doing that and just removing this variable then. Okay, so for some of this, I just switched the allele, so I had to use 1 minus the frequency instead of the frequency. And then it's a good idea to do some quality control on the summary statistic. So you can use at the sample size. So sometimes you have a sample size per variant, because when you get some GWAS summary statistics, sometimes they come from meta-analysis of multiple studies. And these multiple studies may have a different coverage. So a genetic variant may be present in one study, but not in another study. So for this genetic variant, you don't get the full sample size corresponding to the meta-analysis. You get the sample size just corresponding to the studies it was present. So you can actually in GWAS summary statistics get like sample size that are per variant, so different from all the variants. So here I'm just using the UCABABANK, so I'm just using the same sample size for all. It's not a meta-analysis; it's just one study, so it's the same sample size. But otherwise, you can, for example, filter at 70% of the max sample size, and remove all the variants that have a sample size that is too low. Okay, you can also look at the info score, the imputation accuracies. So here in the UK bivalent, the imputation accuracy is quite good. So most of the variants have an imputation accuracy close to 1. So here you can, for example, use 0.7 or even 0.8 or 0.6. And also quickly checking the allele frequencies, and I will use some threshold on the frequencies, not to use two variants that are too with a frequency that is too low. Okay, so this is so some quality control on these numbers that so not samples that are too low compared to the other, imputation accuracy that is not too low, and also the frequency that is not too low. It's something very common to do as a quality control of the summary statistic. And then what I propose to do as well is to check the consistency between the standard deviations. So standard deviations, you can get them in two ways. You can estimate them in two ways. You can estimate them from allele frequencies. So here, for example, what I do, I just compute the frequencies from the data. So to do that, I just compute the call sums, okay, the sum of each genotype, just divide by 2 times the number of individuals, which give me the frequency in the data, the allele frequency in the data. Okay, so I can compute the frequency in the data. Okay, it looks like this. And then I can just estimate. So you remember we talked about this when I talked about Hardy-Weinberg equilibrium. Normally, the standard deviation should be approximately times the frequency times 1 minus the frequency, and then you take the square root. Okay, so I can estimate the standard deviation of the genotypes from the frequencies. Okay, so I can estimate the standard deviation from the allele frequencies, and I can also estimate the standard deviation from the GWAS summary statistic. So for example, when I have a GWAS summary statistic for a binary trait that was computed with logistic regression, you can just estimate the standard deviation of the genotypes from the sample size, the standard error of the effects, and the effect sizes. And then I can just compare these two estimates. I'm just plotting 50,000 points at random. Okay, just to make it faster. Okay, so here I compare the standard deviation derived from the summary statistic versus the standard deviation derived from the allele frequencies in the reference set. And they should be approximately equal. And you can see that there are dots that are very far away from the line. So this you should remove. This all these dots there, all these variants, you should remove them. Okay, so you have this criterion where I say that you need this to be 50% of this. So it can't be above like this line, basically the 50% line. It can't be more than 0.1 on top. So here you have like it can just be 0.1 on top. And then I have some threshold here directly on the standard deviation. So if the standard deviation is too small, it just means that the allele frequency is too small. So I don't want to use variants that are too low frequency. So just a way to filter on the minor frequency. Okay, so here I'm comparing the standard deviation from the GWAS summary statistic. So in the UK background, basically, versus the one from my data to make sure they are consistent. Actually, what you could do that as well from the summary statistic alone, because you get also the frequency from the GWAS summary statistic. So you could check the consistency between the frequencies in the summary statistic and the effect size and standard error of effect size in the GWAS summary statistic. So let's do that. So we can again derive the standard deviation from the frequencies, but now this is the frequencies from the GWAS summary statistics that were in this data, in the GWAS summary statistic that we read. Okay. So just a minor difference. So before I use this, and here I am actually multiplying by the info score, because when you have imputed data, the standard deviation is smaller. So, and it's smaller by basically you just need to multiply by the info score. So it's actually the standard deviation in the original data where the GWAS summary statistics were computed, so the UK Biobank. And if I compare this with the ones that are inferred from the effect size and standard error of effect sizes, I get a very good fit. Which means that all this information that are present in the GWAS summary statistic, they are consistent between each other. Okay. So it's there is no error, apparent error in the GWAS summary statistic. I can tell you it's never the case almost. Yeah. It's just a one line, right? I think it has to do with the covariates, because yeah, like the standard deviation of the phenotype is a bit that is captured in the covariates, and this is just why you get this small difference. But it doesn't matter. Yeah. Okay, so it should be approximately on the line. So here it's fine. It's consistent between the frequencies and the GWAS summary statistic. So what happened before? Basically, what you could do is compare the allele frequencies. So just compare that the frequencies in the summary statistic and the frequencies in your data are the same. And you can see that some are very different. Okay, so there is a large difference between the allele frequencies in these two data. I'm just restricting to this choose a threshold by visual inspection. So here, when I look at this histogram, I will use a threshold of like 0.07 or 0.08 as a threshold, and say if the difference is larger than this threshold, then I suspect that there is an issue with the data, and I just remove the variant because of this difference of allele frequencies. Okay, so now, so basically this doesn't filter anything anymore because the data were very consistent. This again is the filtering on the low frequencies. As I said before, I can filter on the info score, the imputation accuracy. And then the last filter is on the difference of allele frequencies. And I can say larger than 0.07 or 0.08 based on the visual inspection of this histogram. Okay, so this was the quality control of the summary static. So you can find some issues with the summary static by just looking at that. Okay, so we perform some quality control for the summary static. So we end up with this data frame with like only the variants that are matched between these two data sets, plus a bit of quality control. So you can, for example, see that if we look at the frequencies, it's not too small. Okay, so now what we need is some LD, so some matrix of correlation between the variants. And so to do that, we need the genetic position. So what we had before is the physical position in base pair. And you can convert that to genetic position in centimorgan. And it's the recommended window that we recommend is like to use 3 centimorgan because we don't expect variants that are further away, like if you take two variants that are further away from 3 centimorgan, you expect that they are not correlated. So you compute only the correlation between variants that are close to each other because you expect variants that are far from each other not to be correlated. Okay, so here I'm just focusing on the first 4 chromosomes. It's just to make it faster to run the tutorial. You can try with 22 after if you want. So I'm just looping over the first 4 chromosomes. The first thing I do is I compute this correlation matrix. So let's try with chromosome 1. Okay, it's already computed. So again, I'm using this run once, save run to just save the outputs for the next time I want to run this. So when I need here, just look at which of the indices correspond to this chromosome, the chromosome 1. And then the same thing for this is the indices in the sumstats. And then this is the indices in my data corresponding to the data that I have. And then I need the genetic position corresponding to these indices. So here I just pre-computed that for you because to convert between the physical position and genetic position, you need to download some external data that is a bit large. So to avoid downloading these large files, I just pre-computed the genetic position. Otherwise, you can just run this function that would do the conversion for you. It's just downloading like files that are 100 megabytes large, I think. So I just wanted not to do that for the tutorials. But yeah, in real code, just use this function to convert from physical position to genetic position. So let's just use the pre-computed things. And then you can use this snpr function to compute this correlation matrix. And it will compute only the ones that are close to each other. Yes. Yes, need that. Okay, what you get is a sparse matrix. Because what you get actually, I can show you maybe like this. 100, 500. So basically, this is showing only the non-zero values. So because you use some distance, you compute only the correlation in some distance. You only have these values that are non-zero, so the values that are close to the diagonal, basically. And all the other values that are far from the diagonal, they are just considered to be zero. So there are lots of zeros in this matrix. This is why we use a sparse matrix format. Okay, so it's the standard. We get a matrix in the standard sparse matrix format. And what I did, I implemented some on-disk formats, so similar to the FBM, but for sparse matrices. And it's useful because for parallelism, as I said, when you have on-disk format with memory mapping, it's more efficient because you don't have to copy the data. So what I did, I just implemented this FBM for SBM format. You just convert from this sparse matrix to this format on the fly with this as SBM. Okay. So we do that for the first 4 chromosomes. You can run it. I send the materials, right? Do you have all the materials, right? It's this website. You all have access to it, right? Okay, so each time computing the correlation should take about 15 seconds. So it should take 1 minute for the full thing. Yeah, already exists, of course. Where is it? This one. So for me, it was already computed, so it's just printing the time it took. So the time is here. It took to compute each correlation matrix. Okay, from that you get this sparse FBM with 100,000 rows and 100,000 columns. So this is the correlation between all pairs of variants for these first 4 chromosomes. So the correlation between variant 1 and 2, for example, is like 73%, then 47, and so on. Okay, so this is the LD that we need. So this compact format has been introduced in this few months ago, but I think everyone has the version that is larger than this, so it should be okay. We can look at the size of the backing file that actually stores the data. So here I'm dividing by this to get the size in gigabytes. So here it's a small file, so it's okay. In practice, you need to get enough memory to store this file, to have this file in memory, basically to cache this, so that when you use memory mapping, everything can stay in memory, so that the access is very fast and you don't have to access from disk to memory all the time. So here it's a very small file, so you should be okay on a laptop, it doesn't matter. If you use the AppMap3 variant or AppMap3 Plus variant, you might need, I think it might be 30 gigabytes. So you might need to store this plus the results of the function. You might need 60 gigabytes to be able to run the function efficiently. Okay, but for a node on GeneDK, it's very small. The smallest node is like 128, so it should not be a problem to get 60. Okay, so we have the SumStat, we have the LD. Now we can run everything. the first thing that we will run is LD-score regression. So LD-score regression gives you some quick estimate of the heritability. And this will be used as initial value in LDPRED2 auto, for example. So it's just to give you a rough estimate of the heritability to use that as starting values in LDPRED2. So here you get the heritability of 5%. You should check that the intercept is close to 1. Okay, and if you want to use LTPRED2inf, which uses a infinitesimal model, so it assumes that all the variants are causal. All the variants are associated with the disease or phenotype of interest. So it's a very simple model. So for that, you need to provide the AD matrix, the summary statistic, and then some estimate of the heritability that we got from LD-score regression. Then this should be very fast because it's a very simple model. You have just need a solver to solve it, and it should be very fast.
Another question. These are observed cases of distance, right? Not liability.
Yeah.
And is there a function for liability, or would you just do it outside?
Okay. So you have this coef to lib, which you can use to convert from observed to reliability scanner. So what you get from this is a vector of effect sizes. So it's the effects from the predictive model. Okay. So to compute the actual Polygenic score, so the prediction for all the individuals, you just need to multiply your genotype matrix by these effect sizes. So for that, we can use prodvec. So between the genotypes and this vector of effect sizes, you have to provide this incult because you have to say that these are the effect sizes corresponding to these variants in G. Okay. So this is why it's useful to store the indices when we match between the two datasets. We store the indices in each dataset so that we can easily go back to these datasets and use only the indices that were in common between the two. Okay, so I just compute the product between this genotype matrix and this vector of effect sizes, and then I get one vector of predictive value, which is just my Polygenic score. Okay, so one value for each individual. And then I can, for example, look at the AUC between this prediction, the Polygenic score, and the actual phenotype in my data. And I get something larger than 50%, which is then predictive. It's not a very good prediction, but it's still predictive. You can also use PCOR, which stands for partial correlation, where you can adjust for some covariates. So here, if I use null, don't have any covariates. I mean, I could use some covariates. I could use the same covariates as before that we made for the GWAS. I could use the same. I could put them here. And then this will give me the correlation, the partial correlation. Here, just the correlation because I don't use any covariates. This is the 95% interval of the estimates. Okay, so as before here, 25% and 97.5% to get a 95% interval. Okay, so it's a LDPRED2inf, so infinitesimal model. So the infinitesimal model is not very likely. So most phenotypes are not infinitesimal at all. So usually this doesn't work very well. Right?
And it's the one that
No, so it was used a lot in the first version of LDPRE because it doesn't have any convergence issue because it's you have an explicit formula for it. You don't use an iterative algorithm to solve. I mean, you cannot do, but it's not a Gibbs sampler, so you don't have any convergence issue basically. And convergence issue were a huge problem in the first version of LDPRE. So this is why this works better than the others because other models, the non-infinitesimal ones, had some problem of convergence and so on. Yeah.
The one that probably used for the eyesight.
Yeah, I'm not sure. The newest things, I think she used LDPRE 2 Auto. But maybe like 2 years ago, yeah, she would use the LDPRE, the first one, but the infinitesimal, the one from Garnier. Yeah. And then you have LDPRE 2 grid. So the difference here is you test many values for the heritability and proportion of causal variance. So you don't assume anymore that the proportion of causal variance is 1, all the variants are causal. You test, you try many values for this proportion. So here I'm testing many values for the heritability. So I'm using the heritability from L-square regression and then multiply by 1 or 0.7 and 1.4. And actually, if you use a smaller value, you get more robust. If you have some issues with misspecification and so on, it's more robust. So it can be also useful to test smaller values for the heritability. So I test all these 4 values. For the proportion of causal variant, I test values between 10 to the power minus 5 and 1 on a log scale. So here I can try 21 different values. And then I can test, I have this option in LDPRE 2 to get a sparse model or not, meaning that in the predictive, so here in the effects from the predictive model, you would get lots of zeros. So lots of variance would not be used in the final predictive model. So it can be useful to get that as well. So you can use sparse equals false and true or true. And if you use all these combinations with expand grid, you make a combination of all these parameters. In the end, you get a combination of 168 different parameters that you can try. And basically, what you will do is get a predictive effect for all these models. Okay, so you will get many Poisson scores. In practice, for the tutorial, just to be quick, we'll just use a smaller grid with only 16 different combinations. Okay. And then we can just run LDPRE 2 grid. So again, with the LD, the effect sizes, all these parameters that we want to try. And then we can do it in parallel. So all these models, for the 16 model, will be run in parallel. So here I have 4 cores. So like basically each of the cores will do 4 models. Okay. So let's try that. I don't remember how much time it took, but I think less than 2 minutes. Okay, it's like 10 seconds here. So what do you get from that? You get a matrix. So before we got a vector, right? Of effect sizes here. But here, because we have many models, then we get one vector for each model, so we get a matrix. So we get a matrix with 16 columns, which is just the number of models. Okay. We can look at the sparsity, so the proportion of values that are exactly 0 in the model. Then we can visualize the performance of each of these models. So again, we need to derive the polygenic scores. So I'm just, again, making just the product between my matrix and the vector of exercises. So now I have a matrix. I just use mat instead of prodvec. What I get from that is again a matrix because I get polygenic score for each of these 16 models. And then what I compute here is a test for the association between my phenotype, my polygenic scores, and I also add some covariates here, sex and age. I could also use the pieces, for example. And I get the Z score from this association test. Okay, so now the param, I have my 3 parameters. I added the information about the sparsity. So here in this model, because the P was very small, the proportion of causal variant that was assumed was very small, then I got some results that is very sparse. So lots of zeros in this, which can be nice. Then the Z score for the association between my polygenic score and the phenotypes of interest.
I'm sorry if I missed this, but are the polygenic scores standardized? Or I'm just working with the raw values?
They are not standardized, but it won't change the Z score.
What's that, sorry?
It won't change the Z score if you standard.
Yeah.
Yeah. Then I can visualize the Z score for the values of P. If you have many values of the irritability, you get many lines with different colors. Okay, so here the best model would be this one. Okay, so then we can just choose this best model. So here I'm taking the parameters, I'm adding some ID. So just 1, 2, 3, 4, and so on. I'm sorting, if you don't know dplyr, I'm just explaining. I'm sorting by descending score. So now I get the scores, the first one, the largest one first, and so on. But I know the order and the ID. Slice one is just to get the first row. So I just keep the first, the largest one. Pool is just to get the variables called ID. So now I just get 6. And this would be the index of the best model. So then I need to use this index here to just access the column corresponding to this best model to have only then one vector of effect sizes. Okay, so usually you need to split the data into validation and test. So you use the validation set to compute the scores for the many models, choose the best one, and then once you've chosen the best one, you use this best one in some separate test set to test the final prediction of your model. Okay. If I just say this is the Z score for the best, I'm kind of cheating because I'm choosing the best one. You should choose the best in some validation set and then test this final model in a separate test set. Okay. Okay, so this was LD-PRED2 grid where we tested many values for the irritability and proportion of causal variance, which are the 2 main parameters of LD-PRED. And then there is a third version of LD-PRED2, which is called LD-PRED2 Auto, that estimate these 2 parameters, the irritability and proportion of causal variance from the data. So you don't have to test many models, many different values. It just estimates one for you. So here, this is these 2 parameters, like the LD and summary statistic that you need to provide. Here you provide some initial values for the irritability, and I use the L-score regression estimates the initial values for the heritability. And then for the initial values for the proportion of causal variance, I test many different values again on log scale. So it will run many models, we'll see, with different initial values for P. This is the number of iterations, so just use 100 to make it faster. These are two parameters for robustness. And then this is just so that you can run it in parallel. So here we run 30 different models actually with different initial values. So you can just run them in parallel. Okay, so let's try that. So you get so you see I have 4 cores that work in parallel. So 2 are finished and the other 2 as well. So what you get from that, max level, that's 1. Yes. So you get a list of 30 because we got 30 models. So you get a list of 30. And then if we look at one of them, so each model gives you then a list of 12, where you get, for example, so this is the final vector of f(x,y,z) from the model. This is the probability of being causal per variant. This is the half of P estimate. So this is so we had like 200 iterations, like 100 plus 100. So this is the value of P in each of the iterations. So this is the value of the heritability in each of the iterations. And for example, this is the final heritability estimate from this model, the final P estimate from this model. And yes. So you get that you have 30 models, okay? What you can do, or what you should do then, is to filter. So for example, some models, sometimes they diverge or something went wrong. So you need to filter out these models. For that, you can get this statistic. And you want to keep only the ones that are the largest. So I'm just getting the quantile, the 95% quantile of this, and just keeping only the ones that are at least 95% of this quantile. So here you can see I keep almost all of them. There are just 2 of them that I remove because they have some value that is too small, which is yeah, it's too small, but it's quite close to the. Okay, so out of the 30 models, I just keep 28 apparently. Yeah, because there is some randomness in the thing. So normally, if you use set seed 1, try that. And rerun the LD press photo. So the seed is to start with some seed of the random generator, and normally then all the random each time you generate some random number, it should be exactly the same as mine. So we should get the same results exactly. Yeah, but there are some packages that solve that for you, so it should work even in parallel. Yeah. So do you get the same now? Do you get the same? Okay, and to get what we're interested in is the vector of f(x) sizes. So we have 30 models. What we want, we just want one, right? So what we can do, it's just so here we keep only the models that pass this quality control, and we just average. So we get the vector of f(x) sizes for all these models that pass this quality control, and just average them to get just one vector of f(x) sizes. So at the end, I get this just one vector of f(x) sizes. Then I can again just use prodvec to get the final prediction as before. So I get the vector of Polygenic scores. And then I can look at the AUC with the phenotype. Okay, so 3 models. The infinitesimal one that is there just because of the previous version of LDPred. It was used a lot, but I don't recommend to use it anymore because usually it underperforms compared to the other two. You have the grid model. So if you have a validation set where you can try many models and choose the best, then you can use this one. And if you don't have that, then you can use the auto model, which estimates these 2 parameters directly from the data. And then I can quickly show talk to you about lasso sum. So lasso sum 2 is just a implementation of lasso sum. There are just 2 small differences, but the main difference is that now it uses the same exact input parameters as LDPred2. So the LD matrix in this format and the GWAS summa statistic, so that you can run it easily just by doing this. So snip lasso sum 2, you just provide the LD, DL beta, and so there are again 2 hyperparameters in lasso sum 2. So it tests different values, and you can do that in parallel. Here I'm just using a small number of iterations to be fast. So this is basically the same as LDPred2 grid. You get multiple models corresponding to multiple hyperparameters. So what you get is a matrix. Okay, so here I have 40 different models when I run this. I can look at this grid of parameters. So these are the two hyperparameters of the lasso sum model, so lambda and delta, lasso sum 2 model, lambda and delta. So there are many values that are tried here. It gives you the number of iterations it uses before convergence. So here, 51 means that it didn't reach convergence before this max number of iterations. This is the time it took for each model. This is the sparsity, so the number of 0 values that are exactly 0 for the f(x) sizes. So with lasso sum, you can get a vector of f(x) sizes that is very sparse. So here you get almost all of them are zeros, which can be nice. So exactly the same as LDPred2 grid, I can compute the z-score, like the association between all this Polygenic score and the phenotype, visualize this. What? Oh yeah, missed this. Yeah. So what you get is like for different values and lambda, different values of delta, which is the color, you get the z-score. So you can see that here the best model is one of these two. And as before, you can just pick the best model by taking the parameters, adding the ID, sorting by descending score, so to get the highest score. Choosing the first one, getting the ID corresponding to the first one, and using this ID to access in the matrix of FX axis just the one that we're interested in. So in the end, we get just one vector of FX axis. And as you can see, many of them are exactly 0, so you don't use these variants in the model. All these variants, you don't use them. Okay, so when you run LDPrep, you can just run lasso sum 2, and then you can just pick the best model among the one from LDPrep 2 plus the one from lasso sum 2. Just pick the best model overall. Okay, so you can do it like this. Sure. Yeah, and as I said, if you're interested in project score, in LDPrep 2 and lasso sum, you should check also this other tutorial.